3.5 billion miles from Earth lies one of the most captivating objects in our solar system. It's a tiny, icy world with the strangest atmosphere ever studied. It may have giant geysers, underground oceans. There's even a small chance it has primitive life. It's changing the way we look at Earth and our solar system. This is the former planet known as Pluto. Pluto sits on the edge of our solar system, 3.5 billion miles from Earth. Remote but not forgotten, for generations of school children, Pluto is the 9th planet. But on August 24th, 2006, Pluto lost its planetary status. It was reclassified as a dwarf planet.
Pluto doesn't care what we call it. It doesn't care whether we call it it's going to be the same object whether we call it a planet or a dwarf planet or a minor planet.
Pluto has all of the characteristics of the other planets. In the same way that a chihuahua is a dog, just smaller. Dwarf planets are planets. They're a smaller variety.
Pluto sits on an exciting new frontier of space exploration. A state-of-the-art spacecraft is heading towards it at around 1 million miles a day. Scientists hope that it will shed new light on the formation of the solar system and even the birth of our own planet.
Every time we take a spacecraft and go by a new body, it turns into an entire world that is filled with fascinating phenomena that we would have never understood before.
The fact that Pluto is so far away, it's so small, it's so dim, and may represent now a whole new swath of real estate worth of objects, tells us that Pluto has a lot in store for us to learn about it.
Our story starts with Pluto's discovery. By the early 20th century, 8 planets have been discovered. Many assume that Neptune is the outermost. But astronomer Percival Lowell is convinced there is another planet out there, a massive planet whose gravitational pull is disturbing Neptune's orbit. He calls it Planet X, but it proves elusive, and for good reason. The giant planet theory is wrong.
The original motivations for searching for Pluto were based on bad data, basically. They just didn't have enough information then and good enough data to really solve this problem.
By 1929, astronomers at Lowell's Observatory outside Flagstaff, Arizona, have been searching for Planet X for 14 fruitless years. 23-year-old amateur astronomer Clyde Tombaugh joins the team and is given the painstaking task of comparing vast numbers of star-like objects. Tombaugh captures the images onto large photographic plates using a 12-inch telescope, small by today's standard. He's looking for tiny points of light that have moved across the night sky. Stars remain fixed while planets move. Tombaugh continues the search for over a year. Then, examining the plates taken on the 23rd and the 29th of January 1930, a faint object catches his eye. Flicking between these two images, he sees that the object appears to have moved. He checks and rechecks, making sure it isn't a comet or a blemish on the plate. It seems the young astronomer has discovered the astronomical Holy Grail, Planet X.
He also was extremely lucky to be looking at the right part of the sky at the right time. And of course, he had very keen eyes and skillfully able to pick out that small object as it moved across the sky.
Even though the giant planet theory turned out to be wrong, Tombaugh still found a planet. The new discovery is headline news. The planet is named Pluto, after the Greek god of the underworld. Based on their original miscalculation, they believe Pluto is bigger than Earth. Pluto officially becomes the solar system's 9th planet. Today, over 70 years later, Pluto is still pushing Lowell's modern telescopes and leading astronomers like Mark Buie to the very limit of their abilities.
Even with modern day tools, it's a difficult job to find these objects, and you have to look at a lot of sky, a lot of data, use the computers, use all these tools, and we work down at the very limits of what our data and our telescopes can do.
For decades, even the most basic questions about Pluto remain shrouded in mystery. And the most basic of all, its size. The breakthrough comes in 1978 with the discovery of Pluto's largest moon, Charon. It was a stroke of luck, as no one thought Pluto had any bodies nearby. Astronomers were able to estimate Pluto's mass by looking at its gravitational influence on Charon.
Now we know what the mass of Pluto is, and all of a sudden it goes from this vague, poorly known place to now you know something about it and can start putting it in context.
The results are surprising. Pluto is not larger than Earth. In fact, it's smaller than our own moon. Side by side, Pluto and Charon only cover the width of the United States. But for astronomers, the biggest mystery was why Pluto appeared to be on its own. In 1951, Gerard Kuiper theorized that Pluto was a remnant of a once massive belt of objects circling the outer solar system. This region of space became known as the Kuiper Belt.
Kuiper predicted a huge empty space where we see the Kuiper Belt. He thought that Pluto was a massive body that would have swept out all the objects there. And in fact, that's not the case at all.
Back then, Kuiper didn't know that Pluto was too small to have had this dramatic gravitational effect on other bodies. Maybe there was a belt of icy objects out there, just too small for them to see with their limited telescopes.
By 1985, it did seem kind of odd to me, and to other people, I think, that the outer solar system would be a very empty place, where essentially nothing was known except for Pluto.
Mauna Kea, Hawaii. In 1988, Professor David Jewett of the University of Hawaii's Institute for Astronomy begins a dedicated hunt for another object beyond Neptune. Despite harnessing the latest digital technology, the task of looking for a tiny asteroid-sized object at the far reaches of the solar system is a daunting one. A bit like finding a grain of rice on a mountainside, as Jewett demonstrates.
To give you an idea for the scale of the Kuiper Belt relative to the orbits of the planets, I've laid out the solar system using various kinds of fruit and vegetables. So we have a ball to represent the sun. Next to the sun, which is the center of the solar system, we have the rocky planets. So we have to go out to 5 astronomical units, 5 AUs, to find Jupiter, the biggest thing in the solar system except for the sun. Then we go out from Jupiter is Saturn, located at 10 AU. Out from Saturn is Uranus at 20 AU. Uranus is the first of the ice giant planets, and Uranus has a near twin. It's called Neptune. Neptune is over here at 30 AU. And then just beyond Neptune comes the famous Pluto, represented here by a tasty macadamia nut. And Pluto moves in and out from the sun, but it's roughly located at 39 AU. So we'll put that back where we find it. Kuiper Belt starts roughly at the orbit of Neptune and goes out to larger distances. So we can represent that by grains of rice from this bag, which I'll drop on the ground, These are Kuiper Belt objects falling in space, and here they go, but in fact they go very far out. They go out in this direction, and in fact it goes out so far that I can't throw it far enough. It goes out to the hill in the distance, far beyond me.
But in 1988, all this is speculation. It's just a theory. There's no hard evidence of other objects in the Kuiper Belt. Dave Jewett continues believing there have to be more Kuiper Belt objects out there, somewhere. For 4 years, he toils in the thin air of Mauna Kea's high-altitude observatories. He has no idea how big or bright any of the objects might be. Then in late November 1992, he and his colleague Jane Liu spot a faint moving dot in the sky.
It was a very, very definite object, far above the noise, far above the threshold of uncertainty. We're completely sure that we found the first really slow-moving thing in the solar system since Pluto.
And it's small, just 140 miles across. Its diameter is just a tenth of Pluto's.
If we were able to find one body in 0.1% of the sky, which was the case, then we knew there must be something like 1,000 times more objects than we'd found.
Jewett's discovery has astounding implications. Now astronomers know there are potentially thousands of icy bodies, escapees from early planetary formation, orbiting out beyond Neptune. And Pluto is just one of many. Perhaps Pluto is not a planet after all. The discovery of thousands of objects in the Kuiper Belt opens up a whole new realm of planetary possibilities. Pluto no longer marks the edge of the solar system. There are hundreds of objects in the Kuiper Belt waiting to be identified, and astronomers are scrambling to find the great prize, an object bigger than Pluto. In 1998, Professor Mike Brown at the California Institute of Technology joins the hunt. At the Palomar Observatory in Southern California, Brown's team embark on an extensive search.
We had started this project of scanning the skies 7 years earlier, and with the idea that we wanted to see if there was something bigger than Pluto out there. We thought there just had to be.
Unlike Tombau's manual method, the team uses a computer-controlled telescope with digital cameras to take hundreds of images across the whole sky.
Clyde Tombaugh used photographic plates, and he would take 2 photographic plates and compare them and look for something that moves. We now use the digital cameras instead, and the computer does most of the work that Clyde Tombaugh did.
On October 21, 2003, the computer records a snapshot of space and gives it a code: 2003 UB313. But with such a backlog of images, 2 years pass before Brown has a chance to review it. Like Tombaugh, it's now down to his skill and judgment to spot one significant object among thousands.
And suddenly this big bright object appears on my screen, and my very first reaction, what did I do wrong? Something must be wrong here. This can't be right. And I checked everything, and realized, no, this is really there. And I immediately picked up my phone and called my wife and said, hey, I just found a planet.
2003 UB313 is around 70 miles wider than Pluto. And though it's 3 times further out than Pluto, it's one of the brightest bodies in the Kuiper Belt. Astronomers call it Eris.
We knew immediately, once you start discovering other objects beyond Neptune and look at the distribution of their sizes and the rate at which you're discovering, it was just a matter of time before you would find one larger than Pluto. And in fact, that's happened.
I never actually really thought we were going to find that one bigger than Pluto. So it was it was sort of a fun moment.
For Brown, Eris is the discovery of a lifetime. For Pluto, the implications are serious. No longer alone, and not even the biggest or brightest body beyond Neptune, can we still call Pluto a planet? One of the first to publicly question Pluto's status was director of New York's Hayden Planetarium, Dr. Neil deGrasse Tyson.
We first opened to the public in the year 2000, not including Pluto among the ranks of the other principal objects in the solar system. And we got raked over the coals by the New York Times had a page one story saying Pluto not a planet, only in New York. Okay, and then I got like hate mail from third graders, ever since.
Tyson leaves Pluto out from the display because it doesn't fit into his two main planetary categories: the inner rocky planets and the outer gas giants.
Pluto's always been a curious object, primarily because we've known so little about it.
Defining a planet is not as simple as it seems. Take Neptune's moon Triton, for example. Although it's 40% bigger than Pluto, Triton is just a moon. After much deliberation, the International Astronomical Union came up with a new definition. Planets now have to meet three basic criteria. They have to have sufficient mass for gravity to contract them into a sphere. They have to orbit the sun and not some other body, or else they would be moons. And lastly, they have to clear the material around their orbit. Unfortunately, Pluto fails to meet one of the criteria. It does not clear the neighborhood around its orbit. On August 24, 2006, Pluto is reclassified as a dwarf planet.
The word planet hasn't been defined since ancient Greece. Back then there were 7 planets: Mercury, Venus, Mars, Jupiter, Saturn, the Sun, and the Moon. And it was never redefined to accommodate our new understanding of the solar system.
Pluto may have lost its planetary status, but it hasn't lost its intrigue. The more scientists learn about Pluto, the stranger its story becomes. Unlike all the other planets, Pluto's surface is covered with exotic ices, such as frozen nitrogen and methane. There are at least 3 moons orbiting Pluto, a planet 2,000 times less massive than Earth. And Pluto's eccentric orbit is more like a comet's. For almost 60 years, it was also impossible to tell whether Pluto had an atmosphere. And when scientists finally get a chance to look, they discover something remarkable. Pluto's atmosphere is unique in the solar system. It's causing the planet to shrink. Pluto, once an isolated planet, the 9th in our solar system. Now stripped of its planetary status, Pluto is just one of thousands of icy bodies in the solar system's furthest reaches. It might not be alone, it might not be a planet anymore, but Pluto is still intriguing. And as scientists unlock the mysteries of Pluto, they're discovering a world full of puzzles and surprises. Astronomers figured out that Pluto was cold and that its surface was encased by ices, but for 58 years, they couldn't tell whether it had an atmosphere. No telescope on Earth was powerful enough to confirm this basic phenomenon on an object 3.5 billion miles away.
Even using the most powerful telescope available to astronomers, the Hubble Space Telescope, which is a fantastic instrument, Pluto just looks like a barely resolved, very pixelated object. We just can't see much detail.
On June 9th, 1988, NASA's Kuiper Airborne Observatory takes to the skies. Astronomers board this specially equipped high-altitude plane on a journey to the Earth's stratosphere. Their mission is to search for evidence of an atmosphere on Pluto by observing a strange celestial phenomenon. The only way to identify an atmosphere on a remote body like Pluto is to observe it during a type of eclipse known as an occultation. When a celestial object, like a moon or a small planet, passes in front of a star, starlight is sharply cut off if there is no atmosphere present. But if the body does have an atmosphere, the starlight behind it gradually dims as the body passes in front. On board the plane, high-powered telescopic instruments record the critical moment.
There you go. Hey, wow, okay. I think that thing has an atmosphere, guys. Yeah. Yep, atmosphere.
Pluto has an atmosphere. It's similar to Earth's, but extremely thin.
Pluto's atmosphere has many of the same chemical constituents as the Earth's atmosphere, but there's very little of it. If we took all of Pluto's atmosphere and we cooled it down even further than its current cold temperature, and it collapsed onto the surface as a frost or snow, we'd have snow up to the kneecaps.
But how does Pluto have an atmosphere under these frozen conditions? The answer turns out to be linked to its eccentric orbit. Most planets take a roughly circular route around the Sun, but Pluto follows an extreme elliptical path. Its orbit carries Pluto as close to 2.9 billion miles from the Sun and as far out as 4.6 billion miles. By contrast, Earth's distance from the Sun varies by just 3 million miles. Pluto receives almost 3 times more sunlight at its closest point to the Sun than at its furthest point. As it moves towards the Sun, Pluto's surface ices turn into gases. The result is a unique atmosphere. It comes and goes. Mark Buey of the Lowell Observatory in Flagstaff, Arizona, explains that Pluto's strange atmosphere is, in effect, turned off and on by the Sun.
This is a little bit like what the atmosphere of Pluto might be like when Pluto is closest to the Sun. And then as the Sun goes away from Pluto, this is what happens. We're going to stick this balloon into this really cold liquid, and the balloon starts to collapse and shrink and get smaller and smaller and smaller as the pressure of the gas inside goes away. And hold it here long enough, and now I have a totally collapsed balloon. Now you'll notice as I pull it back out, it's starting to warm up again. There's actually liquid air inside there. And the gas starts to expand and swell up. And this is kind of what happens with Pluto's atmosphere, we think, over the course of its year. At perihelion, or when it's closest to the Sun, you have this big atmosphere, and then when it gets furthest away from the Sun, the atmosphere shrinks and could maybe even disappear entirely.
No other known body has such a radically fluctuating atmosphere. And the more scientists study it, the stranger it becomes. Fran Bagenal, professor of astrophysical and planetary sciences at the University of Colorado, thinks that Pluto looks like a comet because it has an atmosphere that leaks into space. Pluto's gravity is so weak that its atmosphere stretches hundreds of miles above the surface.
Similarities with the comet are that the weak gravity of Pluto allow the atmospheric gases to escape. And so, as Pluto gets closer to the Sun, you have greater evaporation and more material escapes. Indeed, it looks very much like a comet in that respect.
When a comet travels towards the Sun's heat starts to affect its icy surface. Ices turn into gases and are blasted away, giving the comet its distinctive tail of ionized gas and dust. Although Pluto doesn't release dust like a comet, it does leak up to half a ton of atmospheric gases every second. And this leads scientists to a startling conclusion. Pluto must be shrinking. Each time it heats up, it gets a little smaller. During our solar system's lifetime, as much as 18 miles of Pluto's terrain may have been lost to space.
And so as a result of this, we expect there to be a considerable variation in the surface, hills and valleys that have evolved over the age of the planet.
Hidden for decades, Pluto's strange surface is obscured to even the most powerful telescopes. But there is a special type of device that can bring it into focus. The infrared spectrometer reads the distinctive reflective signature of Pluto's surface. Using this technology, scientists can piece together a remarkable picture of the strange world of Pluto. Spectrometers tell us that Pluto's surface is covered by exotic ices. Temperatures on Pluto drop to a chilling minus 396 degrees Fahrenheit, so that nitrogen, methane, and carbon monoxide exist as frozen solids. The gases we breathe, see through, and move through on Earth make up Pluto's rocks, plains, and hills. Astronomers think that around 30% of Pluto is made up of ices. Beneath the exotic ice-covered surface sits a water-ice mantle. But is Pluto just a frozen world? As scientists investigate this puzzling dwarf planet, an intriguing possibility emerges. Could there be an ocean hidden beneath its surface? Could the existence of ice and liquid water on Pluto provide further evidence that the Kuiper Belt was a source of Earth's water? Scientists believe that Pluto-like worlds may have played a fundamental role in bringing water, the vital ingredient for life, to Earth. In the outer solar system where the sun's influence is weak, water ice is abundant. But could Pluto also have liquid water? Professor Bill McKinnon of the Washington University in St. Louis thinks so. He believes that beneath Pluto's frozen surface, there could be an ocean. McKinnon believes that water on Pluto could exist in liquid form due to the presence of ammonia, which acts like antifreeze. If he's right, water could remain liquid at temperatures far lower than those of the Antarctic.
Bodies like Pluto can actually have oceans. Not oceans on the surface like on the Earth, but oceans down below. And I have basically Pluto right here in this glass, and I can add the water and something like ammonia that would be inside Pluto.
Add ammonia to water, and the freezing point plummets to nearly minus 142 degrees Fahrenheit.
And to make it look more oceany, although we have no idea what the color of Pluto's ocean would be, we'll add some food coloring. Now out there in space, you're a long way from the sun, so it's cold. And so the top will freeze, like on a lake or in the Arctic, and you'll actually start freezing from the top down, and you'll make a thicker and thicker layer of ice, and I'll start it off by adding some ice at the top, which will float. And then, because we can't actually go into deep space, we'll put it in the freezer. But I put an earlier version of this a couple of hours ago, and this is sort of what you'd actually get. You'd actually see an icy layer floating on, I can jiggle it a little bit, a liquid layer that actually won't freeze.
After 2 hours in the freezer, the ammonia keeps the water liquid. But turn the temperature down below minus 142 degrees, and even ammonia-rich water freezes. On Pluto, surface temperatures are a mind-numbing minus 390 degrees Fahrenheit. At temperatures this low, every drop of water should freeze. So for water to remain liquid under the surface, there must be another force at play. A force that scientists believe lies deep inside Pluto's inner rocky core. Here there may be radioactive substances which generate heat as they decay. This heat could raise Pluto's subsurface temperatures to the critical level where ammonia-rich water can exist. It's a tantalizing theory, because whether in liquid or frozen form, the presence of water on Pluto and its Kuiper Belt neighbors could hold the key to one of our planet's greatest mysteries: the origin of its oceans. One popular theory suggests that comets, which are rich in water ice, may have delivered water to Earth. But Dave Jewett thinks comets may not be the only source of Earth's oceans. Jewett believes Pluto-like bodies in the Kuiper Belt may also have played a part. It would take roughly 1 billion average-sized comets to deliver Earth's water, or one single ice ball 600 miles across. No comet this large has ever been discovered. But in the Kuiper Belt, there are between 50 to 100,000 ice-rich objects larger than 60 miles in diameter, and dozens at least 600 miles across. At the dawn of the solar system, astronomers estimate that the Kuiper Belt was around 100 times more massive than it is today. Sometime in the past 4 billion years, the Kuiper Belt has shrunk.
Several tens of Earth masses, even up to 100 Earth masses of stuff, originally was present in the Kuiper Belt and then was lost by some process that remains mysterious.
Could this loss coincide with the creation of oceans on Earth? This is Neptune, the 8th planet and the Kuiper Belt's closest gas giant. Computer simulations show Neptune's huge gravitational field may have dislodged Kuiper Belt objects, sending them spiraling toward the Sun. Parts of them may have collided with Earth.
We know there was a period of time when there was just stuff slamming in all over the place. And that had to hit the Earth too. It's possible, entirely possible, that those objects were Kuiper Belt objects, which are full of ice and water. Most of the water is hanging out in the outer solar system, and all the rocks are in the inner solar system, but maybe by these stirring events, you can kind of bring these two areas together.
If the theory is correct, objects like Pluto and the Kuiper Belt played a part in delivering Earth's water, vital to all life as we know it. Pluto is slowly yielding its secrets, shedding new light on our solar system. But incredibly, almost 80 years after its discovery, we still don't really know what Pluto looks like. Despite powerful modern telescopes, there are no detailed images of Pluto. These, taken in 1994, are the clearest to date. They were captured by Hubble, the space telescope that escapes the distorting interference of Earth's atmosphere. The largest point of light in the center is Pluto. Its largest moon, Charon, is next to it. To construct a global map of Pluto's surface, Mark Buey turns to Hubble's infrared images.
Each one of these images represents one picture taken with the Hubble Space Telescope. You stitch all those pictures together into a uniform map, which then I can manipulate and make it look like a globe.
This composite globe shows a reddish surface with patches of light and dark, evidence that Pluto has a varied landscape. At the solar system's outer limits, beyond the reach of even the most powerful telescope, Pluto remains shrouded in mystery. But not for much longer.
You either need a bigger telescope or you gotta go there. And so, we're going there.
Right now, a sophisticated spacecraft is racing towards Pluto at around 1 million miles a day. It's ETA 2015. January 19th, 2006. The Atlas V rocket blasts off from Cape Canaveral, Florida. On board, the New Horizons spacecraft. It's on a 9-year journey to Pluto and the Kuiper Belt. This is a voyage into the unknown. Since NASA's inception in 1958, its missions have provided stunning pictures and vital scientific information about our solar system. Some have even involved robotic landing vehicles to examine and explore these new worlds up close. NASA has sent spacecraft to every major body in the solar system, except Pluto. Pluto is still waiting to be explored. In the first ever image of Pluto taken almost 80 years ago, the planet appears as a tiny pinprick of light, no brighter than a distant star. Even the latest images, captured by the Hubble Space Telescope, show Pluto as just a blurred ball of light.
Pluto is so far away and so small that Hubble's capacity to see detail is greatly limited.
To get a sense of what it's like to try and see Pluto, best thing to do is to think about if you were to look at a ping pong ball, someone was to carry it 25 miles away.
An important clue to Pluto's appearance comes from data gathered by another mission to the outer solar system. In 1989, NASA's Voyager 2 skimmed past one of Neptune's 13 moons, the mysterious Triton. This flyby provided astronomers with a tantalizing glimpse of what Pluto might look like.
This icy moon, this large icy moon, that's very much a companion to Pluto, similar size, similar part of the solar system, and maybe had a very similar origin.
Astronomers theorize that many billions of years ago, Neptune slung Pluto outwards and dragged Triton towards it, taking it captive as a moon.
Triton is just like Pluto, but it got captured by Neptune billions of years ago. If we were to fly over Pluto, we would see impact craters and volcanic calderas or collapsed craters, and maybe even active venting or plumes, because we see these things on Triton.
Triton's strange landscape suggests that Pluto could be a dramatic place. And on Triton, the most dramatic features of all are geysers. Voyager 2 captured these remarkable images, evidence of geysers that last for up to a year and spurt gas and dust up to 5 miles high. If there are similar geysers on Pluto, astronomers predict that they would be driven by the sun. Although the sun is over 3.5 billion miles away, its heat may still have the power to affect the ice beneath Pluto's surface, turning it into gas. Pockets of subsurface gas would build up and eventually burst through Pluto's frozen surface as geysers. Will Grundy demonstrates how even a small increase in temperature produces a large geyser.
Okay, we're going to put liquid nitrogen into this plastic bottle, and it's very cold at 77 degrees above absolute zero. So as soon as it comes into contact with the hot environment here with the sun shining and the warm air, it starts boiling like crazy. And as it boils, it's going up into gas. giving off a huge amount of gas. And as soon as I screw the lid on, the gas has nowhere to go except up the tube in the lid and out through this cooler full of ice to form our simulated geyser. And here it comes. On the surface of Pluto, don't know what the scale of those geysers would be, whether they'd be very small like this one or maybe a kilometer tall.
Such mysteries will be solved on New Horizons' arrival in 2015. The spacecraft's camera has already been tested 6 months into its epic journey, capturing perhaps the greatest volcanic eruption ever witnessed in space. "76 years after Pluto's discovery, and after 17 years of research and development, NASA's New Horizons spacecraft sets out for Pluto. Traveling at around 1 million miles a day, it's on a 9-year, $700 million journey to reach Pluto and reveal its secrets. New Horizons chief scientist is Hal Weaver.
Where we are right now is mission control for the New Horizons mission to Pluto. This is where we watch all of the activities that are occurring on the New Horizons mission. We have over here to the left a depiction, the software prediction of exactly where the spacecraft is, where it's pointed. We're following it on its path to Pluto.
In early 2007, New Horizons passes Jupiter, using the planet's intense gravity to boost it toward Pluto. It took the opportunity to test its camera on Jupiter's largest satellite, Io. The results were spectacular. This footage, captured by New Horizons' long-range reconnaissance imager, shows the actual eruption of a volcano on Io's surface.
We were just lucky and happened to catch it when one of the major volcanoes was active. It had spectacular plumes. Debris, volcanic debris, was flying up for a couple of 100 miles above the surface.
It's a stunning but short-lived encounter. New Horizons soon leaves Jupiter behind. Traveling at over 8.5 miles a second, it's the fastest spacecraft ever launched. It's going so fast that after its 9-year journey, New Horizons will only have a day and a half to see Pluto close up before disappearing deeper into the Kuiper Belt.
And that's great for getting there early. But on the other hand, of course, that means that everything is really sped up as we fly by, because unfortunately, we can't just go to Pluto, put on the brakes and stop and hang around for a while. Roughly 3 months out, we're going to have resolution that's better than Hubble, and then it just gets better and better and better as we get closer and closer. But for those last 24 hours where we have this really high spatial resolution where we can see football field-sized features on the surface of Pluto, that all happens very quickly. We're just going to fly by and then just by Pluto and on deeper into the Kuiper Belt.
With such a short window to capture data, the team must test and retest the instruments throughout New Horizons' 9-year journey.
Every year, for about 2 months, we're going to wake the spacecraft up and do some testing. Some observations of celestial objects and some commissioning testing of all the instruments to check them out, to make sure they're still performing and they'll be ready to go when we finally get to Pluto in July of 2015.
Ready to answer some of science's most fundamental questions.
The delivery of organic material and water from the outer solar system to the inner solar system may have played a pivotal role in the formation of life on the Earth.
It's just one of many questions about the solar system and its formation that scientists hope New Horizons will help answer. But above all, when New Horizons arrives, astronomers are expecting the unexpected.
I think the most exciting things that we're going to learn from New Horizons are all those things that it never even occurred to us to ask. And suddenly you go there and you realize, wow, we didn't know anything.
One thing is certain. The arrival of New Horizons will be the astronomical event of the 21st century.
It's a whole new kind of world. It's a planet I think everyone has tried to imagine. It's a frontier world. It's going to be the cover of the Rolling Stone.
And perhaps most fittingly, the spacecraft carries the ashes of the man who started the journey to Pluto almost 80 years ago, Clyde Tombaugh. This is a journey to one of the solar system's most puzzling, most mystifying worlds. Once the 9th planet, now a dwarf planet, an isolated oddity that became one of many. A frozen wasteland that could be home to giant geysers and underground oceans, and even possibly to primitive life. With so many twists to Pluto's story, who knows what surprises lie waiting to be discovered? Waiting for New Horizons' arrival in July 2015. The Rocky Mountains, the backbone of North America. Rugged, spectacular, and majestic. Today, geologists are cracking open these rocks to expose their secrets. How did the remains of sea creatures end up in mountain peaks thousands of feet in the air? When did the Rockies form? Are they still rising today? And if they are, could the great forces that built the Rockies one day split North America in two? The Rockies, one of the greatest mountain chains on Earth. They stretch over 2,000 miles from the northern tip of British Columbia to the Rio Grande in New Mexico. Up to 300 miles wide, they form the Continental Divide, the Great Barrier between East and West. In Colorado alone, there are 58 mountain peaks over 14,000 feet tall. That's around 2.5 miles high. The Rockies were created by the most powerful geologic forces on Earth. Their dramatic story takes us on a journey from north to south through 200 million years of geological history. From their birthplace in Canada to the youngest peaks in the United States. It's a journey that takes us back into the Earth's ancient past. 200 million years ago, there were no Rockies. Even the continents looked different. There was just one giant landmass, Pangaea. But not for much longer. A vast rift is opening up, tearing this supercontinent apart. Over the next few million years, Pangaea will break apart into many smaller landmasses, eventually forming the present-day continent of North America. Earth's surface is broken up into vast pieces called plates. They sit on top of the Earth's warm, dense mantle. As the planet gradually cools, convection currents in the mantle slowly move these plates across the surface of the Earth. Where plates meet at their edges, there are often immense tectonic forces. These tensions can tear continents apart, but they also build mountains. Kirk Johnson, chief curator of the Denver Museum of Nature and Science, explains.
The action of continents crushing together or continents being hit by oceanic plates, those kinds of forces create basically planetary traffic accidents, and the wrecks result in mountains forming.
Evidence of the power of these immense forces can be found in one of the oldest and most northerly parts of the Rockies, Yoho National Park in British Columbia. Here, the fossils of thousands of peculiar prehistoric creatures lie in a cliff face near the peak of Mount Stephen, 8,000 feet above sea level. Geologist and mountain guide Paul McNeil specializes in the fossils of the Burgess Shale.
We see fossils here that we find almost nowhere else in the fossil record, and unlike any animal that's alive today.
This spiny creature is called Hallucigenia. And this bizarre specimen, Wewaxia. These fossils offer clues to how the early northern Rockies formed, because they're not the remains of mountain-dwelling animals, but of sea creatures. They lived and died in a shallow tropical sea over 500 million years ago. The rocks that contain these extraordinary fossils formed on the sea floor.
Right around us, all of the rocks that we see used to be part of an ancient seabed. The limestones were part of the continental shelf. The shales were part of the deeper ocean waters, but it was all underwater.
Long before the Rockies formed, the west coast of North America was covered by a shallow sea. Over millions of years, clay, mud, and gravel settled on this coastal shelf, trapping and fossilizing tens of thousands of sea creatures. Layers of sediment solidified into rock up to 12 miles thick. The rock layers in this cliff are made from sediment laid down over 8,000 years. Today, these fossils are 1.5 miles above sea level. But once they were buried 6 miles under other layers of rock.
At their deepest point, these fossils were buried over 10 kilometers under the Earth's crust. And since then, they've been thrust up to over 2 kilometers up into the air, where we actually find them now.
This ancient rock formed offshore, 400 miles west of here. So what could have driven this ancient seafloor so far inland? And what pushed it up almost 8 miles? A force powerful enough to transform a flat ocean floor into massive mountains. Subduction. 180 million years ago, the North American plate was moving west, driven by the breakup of Pangaea, and the Pacific Ocean plate was heading east. The two colossal plates met head-on. In this clash of the titans, the denser Pacific Ocean plate was forced down beneath the more buoyant North American plate. Professor John Geisman from the University of New Mexico demonstrates.
What I'm going to do is simply tap on one of the sides, and I'm going to create an instability. Now we have oil starting to migrate, move its way over the top of the CD. Ah, voila, it's happening all by itself. I don't have to nudge it anymore. You see the oil moving its way across the CD like so, and the CD itself is going to begin to move like so into the oil, and the subduction process is completed. It's subducted into the interior of our planet, if you will. And it's a runaway process. You can't stop it.
On top of the subducting Pacific plate sat offshore islands. As the plate was pushed eastward, it carried these islands like a conveyor belt. One particularly large island reached the junction of the two plates and coast of North America, but it was too large and buoyant to be pushed down into the mantle. Instead, it slammed into the continental shelf on the western edge of the continent. The seabed was shoved eastward. It slowly folded up like a crumpled carpet. The fossils of the Burgess Shale were pushed thousands of feet into the air and miles inland. geologist and author Ben Gadd has spent 30 years studying the Rockies here in British Columbia.
One way to imagine this whole pushing and shoving business is to do it on your hands. So you have the bony part of your hand, and then you have the skin over the top, right? So imagine that the bony part is the continental plate, and on top of that, you have all the sedimentary layers, right? That's the skin. So when the big push and shove comes, you have the skin being pushed along the bony layer, and as it gets pushed along, it wrinkles up. That's a good analogy for how the Rockies were formed. The older I get, the better this works for some reason.
Over millions of years, the plate collision forced up the northern Rockies. When the force of this collision lost its power, the first wave of mountain building came to an end. But that's not the end of the story. 80 million years after the first block of land hit the coast, a second one slammed into its back. It bulldozed everything eastward and upward. Layer after layer of rock was shoved higher and higher. First into hills, and then into mountains. Gentle folds of rock evolved into the mighty Rockies. Today, these slabs of land, called terrains, make up British Columbia. As they continued to rise, the Rockies were continually sculpted by the momentous force of the elements. Even as they were pushed up, erosion was starting to tear them down. The Canadian Rockies. Jagged peaks, steep cliffs, and razor-sharp ridges, carved from the sedimentary rock of an ancient seabed. Despite being caught in a mighty plate collision and thrust up into towering peaks, the layers of rock in these mountains still lie almost horizontally. This provides a clue about how they rose up. As the blocks of land drove into the coast of North America, slabs of sedimentary rock were pressurized and folded so much that they snapped. Broken sheets of rock, up to a mile thick, shunted forwards and slid over each other again and again, in a process scientists call thrust faulting.
So the rock has actually been folded to the point where it can't be folded anymore. And at that point, the upper part of the fold will literally break and start sliding along. That's what we call a thrust fault. And it's a classic kind of fault for the Canadian Rockies.
Sedimentary rock forms when younger layers of sediment settle on top of older layers. But here in the Rockies, layers of different ages are jumbled up. Thrust faulting pushed older layers of sedimentary rock up and over younger layers.
Suppose that we think of this book as being a continuation of the layered rock that we see here. Now in a thrust fault, what happens is this part will break up and it will slide along like this, and it can go rather a long way until eventually it stops. So now we have layers that were down here pushed up over these layers. Old rock pushed up and over younger rock.
In this laboratory sandbox, the layers of colored sand represent layers of sedimentary rock. As the sand pushes eastward to the right, thrust faults form, one in front of the other. Thrust faulting pushes older rock layers above younger to create the distinctive sawtooth ranges of the northern Rockies. These mountains first emerged 140 million years ago. Thrust faulting first built the western ranges, and then crept eastward, forming a new range further inland. 120 million years ago, the main ranges appeared. And then even further east, the front ranges, 85 million years ago. Thrust faulting began to slow down until eventually, 50 million years ago, it stopped. At Mount Yamnuska, the mountains and the foothills meet. Beyond lie the flat plains of Alberta and Montana. Immense forces pushed an ancient seabed thousands of feet into the air. But a very different force sculpted it into these striking peaks. Erosion. Evidence of erosion's power is strewn all over the mountainside. Piles of broken shale and heaps of ash-colored sediment called scree.
Erosion has been at least as important as the mountain building itself. It's the mountain building process, the uppiling, that gives you the elevation to give you the height of the landscape. But then the landscape itself is carved downward differentially. So erosion is very important. It actually gives us the landscape we see.
Erosion is so powerful that it has scraped up to 2 miles of solid rock off the top of these mountain peaks. And the main force of erosion is water.
Water loosens materials, sends it downhill. Water dissolves minerals. Water freezes and breaks up the rocks.
The northern Rockies are made of sedimentary rock like sandstone, shale, and limestone. Relatively soft and soluble, these are easy prey for erosion. And here in Canada, water's erosive power takes on a new dimension. In this cold climate, snowfall freezes and compacts to form enormous sheets of ice, glaciers. The glaciers here creep forward at 50 feet per year. On a geologic timescale, this is fast. Glaciers pick up and carry loose rocks and boulders, which scour and scratch the rock beneath them. Like giant ice cream scoops, glaciers gouge out distinctive U-shaped valleys. And when they melt, they leave behind deep gorges and steep-sided peaks. Erosion has worn down these rocks over millions of years. But the Rockies are fighting back. While erosion attacks their summits, deep below ground, the mountains are still growing. Look at the Rockies, and it's like seeing the tip of an iceberg. Mountains have roots, which can be 5 or 6 times deeper than their height. This mountain stands over 2 miles high, but its hidden root could extend 13 miles underground. These roots are the Rockies' secret defense against erosion. Structural geologist Carl Karlstrom from the University of New Mexico demonstrates using blocks of ice. The red and green ice layers represent the mountains above ground, and the white ice their roots below ground.
Mountains are not static things. The Earth's surface is continually being reshaped by erosion, by rivers, by glaciers that tear the mountains down. So let's imagine I'm eroding the mountains now, and I'll just pull one of the blocks off. The overall surface has gone down. The continent has gotten thinner, its roots come up, And now this rock, which was deep in the earth a minute ago, underneath the green layer, has come to the surface. That's called rock uplift. So I guess I'll erode off the pink layer too. We're back down to a continent without a major mountain belt, something like the eastern part of North America.
When the heavy weight of the mountain is eroded away, the root rebounds upward. This process means that the Rockies are constantly topped up from beneath. In Canada, thrust faulting and erosion have shaped the mountains. But as we travel south, this distinctive landscape is about to change. Just south of the U.S. border in the state of Montana, a new rock appears among the Rockies: granite. This is the first clue that the mountains of the American Rockies are radically different. On our journey south along the Rocky Mountains, we're entering a very different landscape. From Montana southward, the Rockies are made from ancient granite, 1.7 billion years old. Granite makes up much of the deepest part of the continental crust. That's why geologists call this rock the basement. The Canadian Rockies are built from sedimentary rocks piled up on top of the continental foundations. So why does granite suddenly appear here in the American Rockies? But there's an even greater puzzle. Mountains usually form close to plate boundaries, but the southern Rockies sit a long way from the plate margin. The Front Range in Colorado is 1,000 miles from where the Pacific and North American plates actually meet. Geologists have come up with an explanation. They believe that the subducting Pacific Ocean plate is responsible. Ocean crust had been pushed deep into the mantle beneath North America for 100 million years when something unusual happened. 70 million years ago, the Pacific Ocean plate started to subduct at a shallower angle. Instead of plummeting steeply, it sliced beneath North America horizontally. This change had dramatic consequences.
The big oceanic plate in the Pacific didn't go deep down, it went in shallow like a spatula under a pizza. So something happened 68 million years ago over in California. That plate drives under North America, but instead of diving deeply, it comes in shallow, and 1,000 miles away from the coast, up from the ground sprout the Rocky Mountains.
For millions of years, the ocean plate scraped along the underside of North America. It created friction, breaking up the basement granite of the North American plate and punching it upward. Structural geologist Carl Karlstrom demonstrates.
Because it was at a shallower angle beneath North America, it was scraping along the base of North America. When that happens, it puts the plate under compression like this, because it's being both pushed at the end and scraped along at the bottom. So it squeezes, pushes up the mountains, and it transferred this mountain building from the edge to great distance from the plate margin.
The shallow angle trajectory of the Pacific Ocean plate explains why these mountains formed so far inland. And it also explains the presence of granite. Thrust up through layers of sedimentary rock, the broken granite became the Rocky Mountains of the South. Red Rocks Park, Denver, Colorado. a landscape forged by granite uplift. Kirk Johnson demonstrates how these granite peaks punched up through the layers of red rock around them.
I'm going to use my assistants, Veronica and Ian, to help me explain how the Rocky Mountains in Colorado formed. Imagine, if you will, that Veronica and Ian are composed of 1.7 billion year old metamorphic rocks, the basement rock of Colorado.
Before the mountains grew, layers of sedimentary rock covered the granite.
And then about 68 million years ago, the mountain where Ian is starts to break and lift up and move up. So you see the uplift forming. And what's happening is that layer of sediments being deformed and bent. And these are the flat irons at Red Rocks. As the mountain comes up, overlying sediments are eroded off and deposited into the adjacent basin. And eventually, Ian's granitic back is exposed as the core of the Rocky Mountains. Veronica remains deeply buried beneath Denver, still covered with deep sediments, and the sediments eroded off the uplifting Rocky Mountains.
Johnson is investigating exactly when these events took place. He focuses on the Colorado Rockies Front Range, which runs 350 miles between North and South Colorado. Dating the Rockies requires real detective work. And like all detective work, you get clues by digging up dirt.
Yeah, so it's sort of counterintuitive. To understand mountains, you don't look at the mountains necessarily, you look at the debris from those mountains. So just like a detective would go through a criminal's garbage can, the basin adjacent to the mountain range is sort of a garbage can of the adjacent mountains. The mountain goes up, it sheds all its garbage off to the side, in this case sedimentary rock and fossils, volcanic ash beds, layers of lava. We can look at that garbage and reconstruct the chronology of the uplifting mountain range.
Today, this debris forms layers of sediment 10,000 feet thick beneath the city of Denver. In their mission to date these massive peaks, Johnson and his colleagues search for the tiniest clues, like fossilized leaves and pollen. For Doug Nichols from the Denver Museum of Nature and Science, these microscopic grains of pollen provide a valuable lead.
Pollen can be used to date the uplift of mountains because plants that were living at the time the mountains were coming up were shedding their pollen, which was becoming incorporated into sediment, which was being eroded from those same mountains. And I'm looking for the particular species of pollen that can tell me the age of the sample.
Each sample of sediment can contain thousands of fossilized pollen particles. Nichols examines a single grain. Every plant genus has distinctive shaped pollen. So by identifying the species of plant and its age, Nichols can start to date the exact uplift of Colorado's Rockies.
We pretty well understand that the uplift began 65 to 70 million years ago because we find distinctive kinds of pollen produced by plants that only lived 65 to 70 million years ago.
Sometime during this 5 million year period, Colorado's Rockies began to rise. But geologists can narrow this window even further, thanks to one of the most catastrophic events in history. $65.5 million years ago, an asteroid smashed into the Earth. It wiped out the dinosaurs and left a distinctive line in the sediments by Colorado's Rocky Mountains. This pale yellow layer in the rock contains the remains of the huge asteroid. Because it's sandwiched between layers of debris that eroded off the Rockies, we know that the Rockies must have been up and eroding at the time of impact, 65.5 million years ago. Kirk Johnson specializes in dating fossilized leaves. He uses them to date the Rockies' birth even more precisely. Geologists know that 69 million years ago, Colorado was covered by a shallow sea. But Johnson's fossil leaves show that just a million years later, there were plants here. Johnson combines his findings with Nichols' pollen evidence to come up with a million-year window during which the Colorado Rockies must have emerged. And compared with the northern Rockies, these mountains grew up fast.
We know that 69 million years ago, Colorado was covered by a shallow sea. We know that at 68 million years ago, the Rocky Mountains were up. So sometime in that 1 million period, 1 million years, the Rocky Mountains came up. It may have taken all the 1 million years. It may have happened in 200,000 years. We don't know that yet, but we're working on that particular question.
Although Johnson's team can't yet say how quickly the mountains grew, they are certain of one thing. 68 million years ago, the American Rockies had arrived. As we continue south through the Rockies, the landscape evolves once again. 35 million years ago at the southern tip of the mountain chain, volcanoes appeared among the peaks, triggered by changes deep beneath America. A new explosive era had begun. As we travel south 2,000 miles through the Rockies and forward through their 200 million year history, we reach Albuquerque, New Mexico. Here, a dramatic change deep beneath America triggered the most explosive phase in the evolution of the Rockies. "70 million years ago, the subducting Pacific Ocean plate punched up huge blocks of basement granite, forming the Rockies of New Mexico. "35 million years later, the Pacific Ocean plate began to peel away from the underside of the North American continent. As the ocean plate sunk deeper, warm mantle came into contact with the underside of the North American plate, right underneath parts of the southern Rocky Mountains. Just as the burner on a hot air balloon makes the air less dense, causing the balloon to float upward through the cooler air around it, so warm, buoyant mantle rose up through the cooler, denser mantle beneath the mountains. Carl Karlstrom thinks that this caused the Rockies to grow even taller.
Well, let's think about uplift of mountains in the context of this analogy of a hot air balloon. We're floating high because we're more buoyant than the air around us. And if we want to go up, actually get still higher, we'll just turn on the burner and fire it up, and then the air becomes lighter within the balloon, causing a dynamic or an active uplift. And we can think of that in the context of mountains as if an upwelling of warm and buoyant mantle is actually pushing up the mountains.
But it's not just the mountains that were affected. The upwelling mantle also stretched the crust above. This sandbox simulation demonstrates the stretching process. As the continent pulled apart, the crust thinned and fractured. An immense crevice, called the Rio Grande Rift, opened up in the heart of the Rockies. In parts of the southern Rockies, the crust is over 30 miles thick, but in places beneath the rift, it's just 17 miles thick. This thin crust triggered something dramatic. Under immense pressure from rising heat in the mantle, it gave way. Red-hot magma blasted out onto the New Mexico landscape. And volcanoes punctured the Rio Grande Rift. Scientists believe that hot magma has surged up from the mantle many times over the past 35 million years. These surges led to renewed volcanism in the Rio Grande Rift. But this is not ancient history. The last eruption, just 1,500 years ago, flooded New Mexico with a river of molten lava 44 miles long. Could such recent eruptions mean that hot magma is ballooning beneath Earth's surface today? Could the Rockies of New Mexico still be on the rise? Laura Crossi, a geologist at the University of New Mexico, is on a mission to find out. Working with Carl Karlstrom, Crossi is focusing on a fault where the Rio Grande Rift meets the Rockies. Here, hot springs bubble up to the surface from deep below. Gases in the water can provide a clue to the activity in the mantle.
This point along this fault is a place where these fluids are finding their way to the surface because of the extension, the tectonic activity. We're able to come here and have a window into that deep, deep world, all the way to the mantle.
Beneath Earth's surface, gases are under immense pressure and dissolve in water. When they reach the surface, they escape as bubbles. Analyzing samples of the gas bubbles, Crossi discovers carbon dioxide and traces of helium-3. Carbon dioxide and helium-3 are both byproducts of activity in the mantle. Their presence indicates that deep beneath the surface, rock in the mantle is melting and on the move. Like a rising hot air balloon, hot, buoyant magma is slowly surging up beneath both the rift and the Rockies. This is evidence that here in New Mexico, the Rocky Mountains are far from dead. They could still be growing, thrust higher by rising mantle. Karlstrom believes that in the future, there will be a wider rift and taller, more spectacular Rockies.
I think portions of the Rocky Mountains are going up dynamically, and that they are getting higher, and the Rockies are getting higher, and certainly in the million-year time frame, we will have more interesting, higher, and more rugged mountains, I would predict.
Having investigated their past, geologists are now looking to their future, and it's bleak. The Rockies are doomed, and North America's destiny hangs in the balance. On this journey through the Rocky Mountains' 200 million year history, we've witnessed their dramatic birth and examined their complex evolution. Now we turn to their uncertain future, a future that goes hand in hand with the fate of the whole North American continent. This is the Columbia Icefield in Alberta, Canada, where geologists are already seeing how the mountains are changing. Within 100 years, it could look something like this. Human activity is altering the course of geological history. Increasing global temperatures are taking their toll on the mountain's glaciers. They're melting. Brian Luckman from the University of Western Ontario wants to know how fast. During the winter, glaciers grow. An advancing glacier pushes a pile of eroded rubble ahead of itself, called a moraine. When the glacier shrinks back in summer, it leaves behind this pile of debris in its wake. It's a telltale sign that the glacier is melting away.
Because the glacier over time is retreating continuously, then what you have left are a series of these annual moraine ridges, which mark the furthest point of advance during the previous winter.
Luckman walks between the moraines, using GPS to map the distance between each one. The greater the distance between them, the faster the glacier is melting.
Glaciers are one of the most effective ways to demonstrate to people that the climate is changing. You've only got to come here twice or look at some of the older photographs to realize something radically is changing.
These two photographs of the 3.5-mile-long Athabasca Glacier show how far it has retreated over the past 30 years. And these photos of the Grinnell Glacier in Montana show that America's glaciers are disappearing as well. One day, the glaciers that have shaped these steep-sided peaks and U-shaped valleys will disappear. But water erosion will continue to sculpt these mountains, beating them down and softening their jagged edges.
The future of the Rockies is that they're eroding at the rate of about 0.06 of a millimeter per year. This is based on taking a sample of river water, measuring the sediment in it, and seeing how fast the Rockies are being carried off to the sea.
The relentless force of erosion has sealed the fate of the Rocky Mountains since they first began to rise. One day, they will erode away to nothing.
The Rockies that we see today, the beautiful mountains, why tourists come here, why it's just one of the most dramatic places on the earth, they're eroding away. And so if we look at all the rivers draining off of them, they're full of silt and sand, and that is our Rockies slowly bleeding to death.
The Rockies will eventually dissolve away. But far in the distant future, there could be a final devastating twist to their story. A continent ripped in two. The future of the Rocky Mountains is inevitable. Thanks to the relentless force of erosion, they will one day disappear. But they will leave a legacy: the Rio Grande Rift. A great tear in the Earth's crust that could one day split North America in two. Geologist Mizumi Roy and her colleague Nicholas George, both from the University of New Mexico, are taking part in an ambitious 5-year project. Its aim? To monitor the widening of the Rio Grande Rift. The team is setting up GPS stations along the length of the rift, like this one in remote New Mexico, 3 hours from Albuquerque. The GPS receivers are buried in the bedrock to a depth of around 5 feet. When the Earth moves, the receivers move too. Roy explains.
If you have 2 GPS stations, then you have information about relative motion along a line that connects the 2 stations.
A network of GPS stations allows the team to build up a much more detailed map of the rift's motions.
By looking at the difference between the coordinates between the GPS stations through time, we get a good idea of the relative motion between each of these stations.
The team has set up 24 GPS stations along the Rio Grande Rift. It's early days, but the team expects to find that the rift is widening between 0.5 and 2 millimeters every year. It's a very slow process. But little by little, the continent is being unzipped.
The Rio Grande Rift is a rift system that's causing a continent to split, and if this process continues for tens of millions of years, you could eventually rift the North American continent apart.
There's a lot of indications that there's some action happening. Maybe some more is in the future for the Rocky Mountains, and another few million years and there will be greater tales to tell of active tectonism further to the north, where this Rio Grande Rift is trying to work its way and crack the continent. I think it'll be unsuccessful in that attempt, but it's giving it a good show.
The story of the Rocky Mountains began with the birth of the North American continent. And it could end with its death. One day, the Rio Grande Rift may split a continent. North America might become East and West America. But all this is hundreds of millions of years into the uncertain future. Today, the iconic Rockies are in their prime. The mountains that divide a continent unite us all in admiration. Dramatic and resilient, they will remain the backbone of North America for millions of years to come. Imagine a world frozen solid, encased in ice from pole to pole. No life roams these frozen plains. Only glaciers move across them. This is not some distant planet starved of sunlight. According to a radical theory, this was Earth, 650 million years ago. No one knows what triggered this calamitous freeze. But if it happened once, could it happen again? Imagine the most profound ice age you can think of. Temperatures plummet to below zero, even at the equator. Before long, ice encloses our entire planet. Research suggests that this may have happened not once, but 3 times in our planet's past. Welcome to Snowball Earth.
A snowball Earth is certainly the most extreme climate change we can conceive the Earth having ever experienced.
What would happen if the world froze over today? Massive glaciers creep from the poles, crushing everything in their path.
First of all, the Canadians are going to have to dig much deeper holes when they go ice fishing. Next, the governors of Washington, Idaho, Montana, North Dakota, Minnesota, Michigan, and Maine will probably declare federal emergencies.
Cities grind to a halt. Power lines collapse and water supplies freeze. Cars won't start. Roads are cut off by ice. Buildings strain and crumble under deep drifts of snow. Everything is entombed. Our frail bodies struggle to survive.
I think human society would collapse if a snowball Earth happened again.
The oceans freeze over. Fish die and marine ecosystems collapse. Our food supply becomes exhausted. Any surviving humans are trapped in an icy hell.
we would have a mass die-off of humans simply because we could not grow enough food under these conditions.
Incredible though it may seem, the Earth may have frozen over completely. Scientists are finding clues in unexpected places. The story begins with a mystery. In the arid Flinders Ranges in southern Australia, layers of ancient rock hold unusual stones. These stones are foreign to the area. They are known as drop stones. The drop stones are embedded in an ancient sedimentary sea floor that formed around 650 million years ago. Tim Raub, a geologist at the Californian Institute of Technology, hunts for these drop stones at the Flinders Range.
This is an example of a drop stone, a piece of ancient rock that was dropped into the ancient mud on the sea bottom.
These drop stones are visibly different from the sedimentary bedrock around them. Something powerful must have carried them here. But what? Dan Schrag, professor of Earth and Planetary Sciences at Harvard University, believes the answer is glaciers.
We actually have ice cubes here that we've made with pieces of sand and gravel in them. So these ice cubes are like the glaciers that are taking rocks from the land, and then when we put them in the water, they'll actually melt and the sand and gravel will fall to the bottom, just like the drop stones on the ocean floor.
These drop stones are evidence that at some point, this area was covered in a thick layer of ice. But it's difficult to explain how ice could have covered the sun-baked mountains of southern Australia. Unless the continent itself was in a very different place. The continents haven't always been where they are now. They move very slowly across the Earth due to the movement of tectonic plates. 650 million years ago, around the time the Flinders drop stones landed here, the continents were positioned very differently. Since the drop stones formed under ice, perhaps Australia sat nearer to the poles where temperatures were lower. To locate the position of a continent in the distant past, scientists study the magnetic identity of rocks. Certain sedimentary rocks contain magnetic particles. When the rocks form, these iron particles line up with the Earth's magnetic field. Near the poles, they align at right angles to the sedimentary layers. And around the equator, they align parallel to the layers. Even if the rock moves, the distinctive configuration of these magnetic particles remains the same and provides a kind of geological fingerprint of the rock. Professor Joe Kirschvink at Caltech Pasadena is fascinated by magnetism.
Magnetism is magic. I've even named my eldest child after a magnet, so I enjoy magnetism.
Kirschvink and his team analyzed the 650-million-year-old rock surrounding the drop stones. The results were unexpected.
That part of Australia was within 5 degrees of the equator, and it just was the most weird place to expect a glacier.
But Kirschvink had to be sure that this ancient rock still held its original magnetic signature. If the rock heated up after it formed, its native magnetism would have changed. Back at Flinders Range, Kirschvink's team uncovered clearly striped sedimentary rock that provided proof.
Here, tens of thousands of layers of mud grew one at a time, upward and upward, in a glacial lake at the edge of a 635-million-year-old ice sheet.
When this rock formed, layers of sediment built up in distinctive horizontal lines. By comparing the direction of the layers of sediment with the direction of the lines of magnetism, Kirschvink could determine whether the rock's magnetic signature had changed.
We can explain the process of magnetism with a simple eraser. If the rocks formed on the equator and gained their magnetism very early, we would expect the magnetic direction to be parallel to the bedding very precisely like this. And then, since the rocks are soft, if they get squeezed or deformed geologically, you would expect them to rotate like this, and the magnetism would shift with the bedding. On the other hand, if the rock had been squeezed and deformed first, and then gained the line of magnetism like this, we would see them warped relative to the bedding today.
If the rock still had its original magnetic orientation, the lines of magnetism would follow the lines of sediment. But if its orientation had changed, the magnetism would cut through the sedimentary layers. Raub drills into the formation to retrieve solid cores of the rhythmic rocks. Back in the lab, the team analyzes samples of rock using a custom-built hypersensitive magnetometer. This magnetometer measures the orientation of the magnetic particles in the rock. It confirms that the particles were aligned with the rock layers. Kirschvink was astonished.
Quite frankly, when I saw the original study, I didn't believe it. And what in fact we see is that they're like this, and as the rock was warped, magnetism warped. That proves conclusively the magnetism formed before the rock was solidified.
This discovery seems to provide irrefutable evidence that the glacial rocks formed close to the equator. Paul Hoffman, professor of geology at Harvard University, was intrigued.
So if there were glaciers close to the equator, where the temperature was warmest, one has to assume that there was also ice in higher latitudes where the temperatures were colder.
650 million years ago, Australia sat near the equator. And yet evidence suggests that its arid rocks lay buried beneath ice. And if there was ice at the equator, there would have been ice all over the globe. These dropstones became the catalyst for a radical theory: Snowball Earth. This is a theory about the most extreme ice age imaginable. And if it happened before, it could happen again. Our world has been through many periods of extreme climate change. But some scientists have proposed that 650 million years ago, the Earth may have frozen over completely. This radical hypothesis raises one crucial question: how could it have happened? Kirschvink proposes that the giant freeze was triggered by the same mechanism that lies behind today's global warming, the greenhouse effect. Except 650 million years ago, it worked in reverse. Greenhouse gases in our atmosphere act like an insulating blanket, trapping the sun's energy to keep Earth's temperatures mild. When the snowball began, scientists suspect that levels of these vital gases fell dramatically.
The Earth's atmosphere might have been filled with methane and carbon dioxide, and the Earth became addicted to this high-level carbon dioxide and methane in order to keep its temperature. Then, if some unknown event crashed the carbon dioxide out of the atmosphere, Earth might have run away into a snowball Earth.
If enough carbon dioxide had been pulled out of the atmosphere, an anti-greenhouse effect would have plunged the Earth into a deep freeze. But this theory is only possible if there's a mechanism that could pull all the CO2 out of the air. In fact, carbon dioxide is removed all the time through a process called silicate weathering.
Weathering is a geological term for the decomposition of rocks under the influence of the weather. It's a process that converts solid rock into soil. Now, its importance for the climate is that weathering consumes carbon dioxide, which is a major greenhouse gas in the atmosphere.
Carbon dioxide reacts with water vapor in the atmosphere to form carbonic acid rain. This acidic rain weathers limestone on land and carries away the eroded sediment to the sea. Here it builds up, eventually forming limestone on the sea floor.
So the presence of the limestone is the evidence that weathering is occurring.
The more carbon dioxide gets locked away in limestone, the cooler the Earth becomes. But if this is happening all the time, something must have amplified the process for the whole world to have frozen over. Again, clues lie in the position of the continents. The movement of tectonic plates continually shifts the continents around the globe. Today, a lot of the continents are located in higher latitudes. If the Earth cools, the continents near the poles ice over. The ice prevents the rocks beneath from being weathered by carbonic acid rain. This means that the weathering cycle is kept in balance. With less carbon dioxide locked away in limestone rock and more in the atmosphere, the planet warms. Scientists have worked out that 650 million years ago, the continents were clustered around the equator, where it's warm and wet. Consequently, the global rate of weathering would have been higher.
During the snowball Earth, we suspect that there were many more continents at the equator, and this would actually lead to a situation that would make the planet vulnerable to a global glaciation.
As the Earth cooled, ice formed at the poles, but because there were no continents in the higher latitudes, ice accumulated on sea rather than on land. There was nothing to regulate the weathering. The cooling continued unchecked, and the world got colder and colder. This runaway scenario is certainly plausible. But although extreme weathering could be behind an ice age, it doesn't explain how the Earth could have iced over completely. Geologist Galen Halverson from Adelaide University studies triggers of the snowball.
One of the hardest parts about understanding the snowball is really how it began. We think that it must have began like a normal glaciation.
Normally, living things help to regulate the Earth's climate by maintaining the delicate balance of carbon dioxide. Plants consume carbon dioxide. Animals produce it. These consumers and producers help to regulate the climate, ensuring the Earth is neither too hot nor too cold. If there's more carbon dioxide in the atmosphere, it gets warmer. This causes plants to grow faster, which in turn draws out more CO2 from the air.
So that is a feedback against it getting too warm. And in reverse, if it starts getting too cold, then the biosphere responds by not drawing down as much CO2, and that allows CO2 to go back up. So there's a sort of buffer in the form of life on Earth that prevents temperatures from getting too cold or from getting too hot.
But rewind 650 million years and witness a very different story. Life on land was in its early stages of evolution. Most living things were in the oceans. This half-formed biosphere could not prevent the Earth from swinging to wild extremes of temperature. Colonies of single-celled organisms called cyanobacteria were the first to photosynthesize. They pulled carbon dioxide from the surrounding water to precipitate calcium carbonate, and they used this to make dome-like structures of rock. Geologist Jim Gehling is an expert on these early life forms.
Temperatures were dropping at this time, 650 million years ago, for the very good reason that carbon dioxide, the principal greenhouse gas, was being taken out of the atmosphere and locked away on the seafloor.
This trapped carbon dioxide can still be seen today in stromatolite reefs.
This is actually solid carbon dioxide, and I can release that carbon dioxide after all those hundreds of millions of years when I put this weak acid on the rock. And there you see it erupt as the white bubbles of carbon dioxide spring out of the rock, go back into the atmosphere to take up their role all over again as greenhouse gases.
The more carbon dioxide the cyanobacteria locked away, the cooler Earth became. Our planet was hurtling towards a deep freeze that would last for millions of years. $650 million years ago, the Earth's temperature plummeted. Huge sheets of ice spread across the planet. Eventually, they engulfed most of the land and sea. This was no regular ice age. Ice ages are nothing out of the ordinary. We experience them every 100,000 years or so. They are mainly caused by small changes in the Earth's orbit, which alter its position relative to the Sun. When our planet receives less of the Sun's energy over a number of years, ice forms high in the northern hemisphere and advances down. At the height of the last ice age 21,000 years ago, these icy sheets reached down as far as New York. But the tropics stayed warm. Only about 30% of our planet froze. But 650 million years ago, some scientists believe the ice kept coming, until eventually, most of the globe was covered. What could have caused this runaway cooling? The answer must lie in how our planet keeps or loses the sun's energy. The Earth's surface is made up of land, open ocean, and ice. These all reflect sunlight to a different degree. The amount of light a surface reflects is known as its albedo. Deep dark ocean has a low albedo, since it absorbs a lot of sunlight. White snow and ice have a very high albedo, since they reflect more of the sun's energy back into space. Tim Raub demonstrates how dark and light colors heat up under the sun.
The temperature of a white car sitting in the sun is only 120 degrees. The temperature of a black car sitting in the sun is 144 degrees. The black car absorbed light, the white car reflected it.
White reflects more sunlight, keeping whatever it's covering cooler. The more ice that covers the Earth, the more of the sun's energy reflects back into space, and the colder the planet becomes. This cooling leads to more ice forming, which further increases the surface albedo. This is known as ice albedo feedback. And something may have accelerated this cycle of cooling even more. New research suggests that when seawater freezes at very low temperatures, its composition changes, and it can become more reflective. At the University of Washington's Polar Science Center, Bonnie Light studies the relationship between ice and light. In the cold room, she freezes buckets of salt water at different temperatures. One of the buckets is exposed to snowball Earth temperatures of -10 degrees. The surface of this ice becomes much whiter.
Okay, so this bucket contains seawater that was frozen in a cold room at 5 degrees above 0 Fahrenheit. And we consider this a good laboratory analog for modern day sea ice on planet Earth. And you can see that the surface of it is kind of gray colored, dull appearance. And this bucket also has salt water in it, although this salt water was frozen at about 10 degrees below 0 Fahrenheit. And we consider the ice in this bucket to be a good analog for sea ice on Snowball Earth because it's very cold.
At Snowball Earth temperatures, the composition of sea ice changes, turning its surface from gray to bright white.
And you can see that these crystals in this case have started to collect at the surface of this cold ice. And so I can kind of scratch away these crystals, and you can see that this is basically just a deposit on the surface of this cold ice.
At -10 degrees, salt molecules in the ice begin to form tiny crystals.
If you can isolate them under the microscope, they look like little gemstones. They're really quite beautiful.
These bright crystals have a dramatic effect on albedo. The white surface scatters more of the sun's energy and reflects it back to the atmosphere, causing temperatures to drop even further. In the 1960s, Soviet climate modeler Mikhail Budiko demonstrated how runaway ice albedo could cause a cooling Earth to freeze completely. Like many of his contemporaries, Budiko was worried about the effects of a nuclear winter. Nuclear explosions create clouds of smoke and dust, which block the sun's energy and lower the Earth's temperature. Budiko developed a mathematical model to work out the odds of a global ice age. He showed that if the Earth's climate cooled enough for ice to form in the lower latitudes, then the ice albedo would rise at a faster rate. And once the glaciers reached a certain latitude, the Earth would tip into a snowball-like state.
Somehow or the other, the ice line, the glaciers, reach some critical latitude, around 30 degrees. And once they hit that latitude, very, very rapidly, the Earth would have been entombed in ice.
Budiko's groundbreaking work showed how this snowballing effect could create a totally frozen planet within just a few decades.
Budiko's work was extremely important in demonstrating that it was possible that Earth might slip into a climate catastrophe which was covered completely with ice. It had not been recognized as a possibility before that.
If the Earth became entirely covered in ice, nearly all the heat it received from the sun would be reflected back into space. The planet would become locked in ice. So if runaway freezing trapped the Earth in ice, how did it ever escape? Some scientists suggest that 650 million years ago, our entire planet was locked in an extreme ice age. It was a unique event, the result of a set of improbable triggers. Or so they thought. Then, in 1997, evidence emerged that it could have happened more than once. It came from glacial deposits in South Africa that were over 2 billion years old. Paleomagnetic evidence suggests that these formed near to the equator. Geologist Paul Hoffman believes this could be proof that the Earth froze over completely at least twice in its history.
The best evidence for a snowball Earth 2.22 billion years ago is paleomagnetic evidence from South Africa. There are glacial tills there, boulder clays, that formed very close to the equator.
This discovery raised the possibility that the snowball wasn't a single event, but a recurring condition. Scientists raced to find the trigger for this earlier deep freeze. The cooling appeared to coincide with the Great Oxidation Event. Deep in the ocean, some of the oldest organisms on Earth evolved a mechanism called photosynthesis. The ability to convert carbon dioxide into oxygen using the sun's energy. As these photosynthesizing microbes thrived, they had a profound effect on the Earth's climate. 2 billion years ago, our sun was weaker. Our planet relied on greenhouse gases like carbon dioxide and methane to maintain its temperate climate. But photosynthesis uses up carbon dioxide. It also produces oxygen, which destroys methane. The result, a double whammy. Levels of both these vital greenhouse gases plummeted.
You have a precarious situation. You have a planet that's greenhouse needs methane, and you suddenly evolve a bug that destroys the methane.
Maybe the first bacteria that photosynthesized crashed the carbon dioxide and methane from the atmosphere and triggered the first snowball Earth.
As oxygen production soared, methane levels tumbled. With the loss of that greenhouse gas, the Earth spiraled into a deep freeze.
It's kind of a frightening conclusion that a single-celled mutant bug destroyed an entire planetary ecosystem. Destroyed it. Turned it into a snowball for maybe 35 to 100 million years.
Some scientists now think that our planet has been encased in ice on at least 3 separate occasions, and each time under different circumstances. But these snowball Earth scenarios present a huge problem. If our planet was trapped in ice, how did it ever escape? Something must have caused a global meltdown. Evidence of the thaw is right here. On top of the dropstones sit layers of a peculiar reddish-gray rock. These layers stretch for miles in the Flinders Range, Death Valley, and almost everywhere where the glacial rocks appear. These are carbonate rocks, which form in warm, shallow seas. But here, they appear right on top of the glacial deposits.
So here's a sample that actually shows the end of the snowball event. So that's an ice-rafted stone dropped out of an iceberg. And these are little grains that also fell out of an iceberg. And immediately on top of that, without any break in sedimentation, is cap carbonate that's precipitating directly out of the ocean and accumulating on the seafloor. And exactly the same relationship is seen all over the world.
Their presence is evidence of a sudden and drastic temperature increase. Only one thing could have triggered this: a huge injection of greenhouse gases such as carbon dioxide. In order to melt snowball Earth, concentrations of carbon dioxide had to be around 350 times higher than they are today. But if the whole planet was encased in a thick layer of ice, where did the carbon dioxide come from? Caltech professor Joe Kirschvink had a revelation.
I woke up in the middle of the night and said, that's gotta be it. It just dawned on me that these subaerial volcanoes, like in the Aleutians and the Yellowstone, these volcanoes sit and they spew CO2 into the air.
Even beneath the ice, volcanoes would have continued to release immense volumes of carbon dioxide. With the rest of the planet still ice-locked, there would have been no mechanism to remove it from the atmosphere. Over millions of years, levels of this greenhouse gas would have built up, eventually producing enough warming to offset the ice albedo. The ice melted, sending global temperatures spiraling upwards. As this melted ice water evaporated, it swelled the atmosphere with moisture, creating torrential rainfall. Carbon dioxide in the atmosphere acidified the rain. Acidic downpours rapidly eroded limestone, washing sediment down into the oceans. Here, layers of carbonate sediment accumulated on the sea floor to become carbonate rock. Dan Schrag demonstrates what could have happened.
Instead of carbonic acid from carbon dioxide, we're going to use a little stronger acid to make it go a little faster. This is nitric acid, and when we add it to the limestone, it will dissolve away the limestone and ultimately create a very clear solution. So you can see it bubbling away. And when this is added to the ocean, it reacts and creates the cap carbonates that blanket the top of the glacial deposits.
But still, not everybody is convinced that the planet was ever entirely covered in ice. Some scientists argue that the chances of life surviving a full-on snowball are virtually nil. Above the ice, the freezing conditions were too hostile, while below it, life was cut off from sunlight. Yet there is evidence that photosynthesizing organisms did survive the freeze. Single-celled cyanobacteria existed right the way through. Cyanobacteria can survive extremes of temperatures many degrees above and below zero. But if the oceans froze over, a thick layer of ice would have sealed them away from the sunlight. With their energy source blocked, they would have died out.
If you'd been diving on a tropical reef before snowball, this is what you would have seen. Slime world, mounds of slime on the sea floor. And if you touch them, you'd find out that they're actually rock. A surface covered with slimy material, which is actually cyanobacteria, the earliest, the most primitive form of life that's been around for 3 billion years up until this point and is still around today.
Critics argue that nothing could have survived the ferocious conditions of a total global freeze. They maintain Snowball Earth was nothing more than a severe ice age with extensive glaciers and a belt of open water around the equator. Philip Allen, a geologist at Imperial College London, believes that the evidence for a frozen planet is flawed.
I am not in agreement with this snowball Earth hypothesis. The major hole in the theory, as far as I'm concerned, is that the sedimentary rocks deposited during the glacial periods do not support the idea of a long-term global freeze.
Philip Allen's counter-evidence includes the ripple-like patterns in rocks formed 650 million years ago.
When you look at those sedimentary rocks, it indicates open water. The wind was able to blow over the water surface and form ripples, wave ripples on the seabed. So they are really conclusive proof of an open water surface rather than an ice-covered one.
Waves in an open sea left imprints in the sediment of the sea floor. When the water disappeared and the sediment turned into rock, the ripples remained. Allen and others propose an alternative to the snowball Earth. It's known as the slush ball. In their version of events, the Earth never froze completely. Some patches of open land and sea remained. But proponents of the snowball theory don't suggest that the frozen planet was without any open water. Schrag believes that life could have survived in ice holes around sources of geothermal energy.
Even in a completely ice-covered planet, there's still plenty of places where there are hot springs, geothermal heat from volcanoes, probably thousands and thousands of such little holes. And in many of those little holes, you could sustain life throughout the snowball Earth period.
The reality is, we may never know if the world was ever completely frozen over.
Sometimes people think of the snowball Earth like a cartoon, an oversimplified planet. But the real world is much more complicated than that.
Whether slush ball or snowball, everyone agrees there was a profound global freeze. And when our world emerged 635 million years ago, something unexpected appeared. Life. Far more complex than anything that had gone before. After the big freeze, life on Earth exploded. Our planet, 650 million years ago. Temperatures plummeted, turning our planet into a hostile place. Yet somehow, life survived. And as soon as the frozen Earth began to thaw, it blossomed. And there was an unprecedented explosion of life on Earth. Before the deep freeze, life was primitive. Single-celled organisms and algae were mostly confined to the oceans. Shortly after it ended, the first multicellular animals appeared. The big question is, did the global cooling trigger this great leap in evolution?
Well, the best evidence is the coincidence in timing. The fact that the first fossils of multicellular animals occur less than 3 million years after the last snowball termination.
Shuhai Xiao is a geologist at Virginia Tech. He unearthed some of the oldest multicellular animal fossils in the world in a mine in southern China.
The fossils are really small. They're about ½ millimeter in diameter, so you can barely see them with naked eyes.
Under a microscope, he discovers that the fossils are very primitive animal embryos. Some fossils show clusters of 2, 4, 8, and more cells.
It was really exciting when we found those. Those are some of the earliest animal fossils, and they have found in rocks that were deposited almost immediately after the snowball Earth ended.
Fossils of these animal embryos date back to just 3 million years after the global freeze ended. That might seem a long time in human terms, but geologically, it's the blink of an eye. Over the next 80 million years, animal life exploded. In the Flinders Ranges in southern Australia, geologists have found some of the oldest fossil evidence of complex multicellular life. These creatures bear little resemblance to life today, but they offer clues to the genesis of early life. 650 million years ago, this area was beneath a shallow sea. Bizarre, soft-bodied organisms similar to jellyfish or flatworms lived on the sea floor. Some of the organisms got trapped in fine silt of tidal flows where they fossilized. Jim Gehling has been investigating these early animals.
Probably our ancestors lie in these rocks. This thing here, Dickinsonia, can best be described as some kind of a pancake or mat-like worm creature. It doesn't have a proper head. It has what appears to be a gut, very fine segments.
But this doesn't explain how the severe planetary freeze could have triggered a leap in evolution. What we do know is that there is a striking coincidence between the rise of oxygen and the end of the snowball. Oxygen levels rise following these global ice ages because of a chemical reaction between ice and sunlight. 650 million years ago, there was no ozone to stop the sun's ultraviolet light hitting the Earth's icy surface. This UV light reacted with water vapor to form hydrogen peroxide. The hydrogen peroxide remained in the ice for millions of years. But when the ice melted, the hydrogen escaped, and the peroxide converted into water and oxygen. Oxygen reached the same level as we have today. At roughly the same time, the first complex animals appeared. More oxygen enabled life to become multicellular. A single cell can take up gases and oxygen from water. Oxygen fuses across the cell membrane into the cell. However, when several cells link together, it's harder for oxygen to diffuse from one cell to the next. The pressure of oxygen needs to be higher.
You need to have a high enough pressure of oxygen to have a circulatory system bring the oxygen all around the body. After the last snowball Earth, oxygen seems finally to have been high enough to support hundreds, thousands, millions of small early animals on the seafloor.
Oxygen turned out to be the linchpin of evolution. The ability to use oxygen enabled life to become dramatically more diverse.
Oxygen gives us 20 times more energy, or more than 20 times more energy, than any other thing that we can breathe, or that life can breathe. You can have bigger animals, you can have more active organisms, you can have plants that grow and transport liquids from roots to the leaves, and you can have birds energetic enough to fly. Without oxygen, we would all be slime.
A frozen Earth may have given early life a push forward. But if the world were to freeze over again, we'd struggle to survive. We know it's happened several times before. The question is, could it happen again? One factor in our favor is the sun. Over the last 4.8 billion years, it has been getting more and more active as nuclear fusion generates more and more heat. The sun today is about 6% warmer than 650 million years ago. So in the short term, another deep freeze is unlikely.
The sun is warmer today. That probably helps us out. But until scientists really understand what causes snowball Earths, I don't think any of us know whether we're in danger or not of a recurrence.
But there is one possibility that could result in another global freeze: a shift in the position of the continents. We know their arrangement influences the climate. If the majority of the continents were clustered on or near the equator, the Earth would be more likely to turn into a snowball. Cooling temperatures would cause ice to form in the open ocean of the poles, while weathering would continue on the continents. With more and more carbon locked away, temperatures would plummet.
If all the continents were near the equator, then the Earth could get colder and colder, and sea ice could form and get to lower and lower latitudes, closer and closer to the equator.
Today, our world seems safe. Most of the continents are near the poles. But plate movement never stops. At some point, millions of years in the future, the continents may group around the equator once again.
I think it's possible someday, if the continents were in a very different position, maybe hundreds of millions of years from now, that we could indeed have another snowball Earth.
It's unlikely that mankind will be around to witness another snowball Earth. But the Earth will still be here. And just like it has in the past, our planet will survive and enter a new phase in its extraordinary history. In the empty blackness of space, surrounded by hostile planets and freezing vacuum, planet Earth is an oasis of life. And all because of our protective cocoon of gas. This blanket of air shapes everything we see on Earth. It protects, insulates, and sustains us. It carries water around the globe and shields us from cosmic impacts and killer radiation. It's time to uncover the invisible wonder that is our atmosphere. Down here on the Earth, we rarely give much thought to our atmosphere. Because we can't see, smell, taste, or hear it, we take it for granted. But our air is all that stands between us and the vacuum of space.
We've got this canopy that provides us a lot more than just an atmosphere to breathe in. It definitely shields us.
The atmosphere is divided into 5 distinctive layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer is less dense than the one below, stretching miles above our heads.
How far out it goes is depending on which scientist you talk to. Some say it ends at 300 miles, some say it extends out to Mars.
We live in the layer closest to the ground. Here in the troposphere, the air is thickest and the pressure greatest. Our bodies are perfectly matched to these conditions.
Our chemistry, our very nature, our metabolism is completely shaped by the atmosphere.
To appreciate our atmosphere, we'll rise through its layers, traveling from the planet's surface, miles up above the mountains and the clouds, to the very edge of space. August 16th, 1960. One man is preparing for a record-breaking journey into the mysterious skies above, to a lethal world above 99% of the Earth's air, where an unprotected human would die in seconds, where the temperatures plunge to 67 below, and the air pressure is 1/100th of that at the surface. Colonel Joseph Kittinger will travel almost 20 miles high, and then he will jump. This is a key military mission, one of the first steps in the space race. Kittinger will be testing the human body's resistance to high altitude, low pressure, and rapid free fall. He will be trialing new technology he hopes will protect him.
It had never been done before, but we were not there to set a record. We were there to gather information that we needed for our space program and for our high-flying aviators.
Ground crew prepares his vehicle, a helium balloon, and a rudimentary open-sided gondola.
Just an open gondola. It was designed just to carry me up there. It was a space platform, an elevator, I called it.
At 5:30, Kittinger's preparations are over. He boards the gondola.
My crew chief said, "Are you ready?" I said, "I'm ready, let's go." It was a very smooth takeoff, and I started ascending. Up, up, up.
30 minutes after takeoff, Kittinger reaches 29,000 feet, the middle of the troposphere. At this altitude, the air is so thin that each breath contains only 1/3 of the oxygen found at sea level. Kittinger breathes from gas bottles connected to his sealed helmet. He's still barely 1/3 of the way to the jump point. There are another 14 miles to go, and the air pressure is dropping rapidly.
So at about 40,000 feet, suddenly the pressure suit starts inflating. And that's when you start checking it to make certain that it's working properly.
But there is a crucial fault in the suit. The glove covering his right hand is not sealed.
I had an option to tell the ground that I had the problem, and I knew that if I did, they'd probably make me abort the flight. And I was concerned that if we had to abort that flight, that we would have been turned down to try to do it again. So I didn't tell them.
Kittinger prays that this is an isolated fault and continues to climb at 1,000 feet per minute. After 89 minutes, he approaches his target altitude. The balloon's climb slows and then stalls. Kittinger is in the mid-stratosphere, a record 102,800 feet high. And it is now time to make the long, swift journey down.
When it came time for me to jump, I was ready to jump because I was heading back toward a more friendly environment, a friendly planet that we're used to. I had made this jump 1,000 times in my mind. I'd gone through every step 1,000 times. Well, just before I jumped, I said a silent prayer. I reached over and hit a button that started the cameras going. And then I just did a little hop off the step of the gondola. can't tell that you're going fast, you can't tell anything. And I looked up at the balloon, and the balloon was firing into space. And I said, gosh, that's amazing. And then I realized it was me that was going down at a fantastic rate, and the balloon was standing still.
He falls for 16 miles. The thin air offers almost no resistance. He reaches 614 miles an hour, approaching the speed of sound. After a record-breaking 4 minutes and 36 seconds of freefall, Kittinger opens the main parachute. He drifts down to the desert floor and lands.
We were just elated because we had accomplished what we set out to do. There was a lot of people who said we couldn't do it, and we proved that we could do it.
The mission has been a stunning success. Kittinger's skydiving record stands to this day. He takes his first deep breath of air with a newfound appreciation for our atmosphere.
It was a relief to be back on the planet Earth that we love so much. A planet that has an atmosphere that we can live daily.
Kittinger forged a dizzying path through the atmosphere. Our journey begins just a few feet off the ground with the air we breathe. We take for granted Earth's blend of gases, the perfect mix for heat and energy. And astronomer David Grinspoon believes we'd be hard-pressed to find its equal anywhere.
The more we learn about planets, the more we learn that they're all individuals. They're like people in that sense. So as far as what we know now, Earth's atmosphere is completely unique.
In the past century, telescopes and space probes have uncovered the extreme atmospheres of our neighboring planets. A journey across our solar system reveals exactly how unusual Earth is. Clouds of near-frozen gas flow over the icy surfaces of Uranus and Neptune, while the sun has blasted away the atmospheres of Mars and Mercury.
To me, it seems as though Mercury doesn't have an atmosphere at all. But in fact, if you were on the surface of Mercury, it would look to you as if you were out in outer space.
In contrast, Jupiter and Saturn are all atmosphere.
Unlike Earth, Jupiter doesn't really have a solid surface that you could stand on and then have your head up in the atmosphere looking at the clouds. It's just a giant, giant gas ball.
Only one other planet shares the Earth's thick atmosphere and rocky surface: our near neighbor, Venus. But even here, there are striking differences. Dr. David Crisp has spent 20 years studying Venus's acrid air.
Imagine you're at the surface of the planet Venus. You're at pressures that are high enough to crush a nuclear submarine. The pressures there are about 90 times the pressure of the Earth's surface.
This pressure is combined with extreme heat, 900 degrees Fahrenheit, hot enough to melt lead. Clouds drift over the baked surface, but they are not water vapor. Venus's clouds are made of concentrated sulfuric acid. Venus is a stark example of how extreme an atmosphere can be. But the real mystery isn't why Venus is so hostile, but why Earth hasn't followed the same path.
As planets go, Earth and Venus are essentially twins. They're almost exactly the same size. They're also very close together in the solar system. In spite of that, their environments evolved in dramatically different ways.
To discover why these twin planets followed separate paths, and to explore what gave us our precious atmosphere, we have to travel back. Back 4.5 billion years to the birth of the solar system itself. The birth of the solar system created Earth's earliest atmosphere. Huge quantities of material orbiting the Sun fused together into protoplanets. Jupiter and Saturn formed into gassy spheres. But on Earth, most of the material condensed into a molten core. The remaining gases bubbled forth from the liquid rock, forming the first atmosphere. Our planet's gravity stopped these gases from drifting off into space. But Earth now had to face the ravages of the solar wind, a stream of charged particles thrown out by the Sun. This same wind had a catastrophic effect on Mars. It has stripped the air from the planet's surface, blasting it deep into space. The red planet's atmosphere is now only 1/100th as thick as Earth's. Our planet was spared this fate. The magnetic field generated by the Earth's core blocked the solar wind, preventing it from blasting away the fragile air. But the Earth's atmosphere was still very different from the one we breathe today. It contained high levels of carbon dioxide, a gas with a key ability to absorb and hold on to heat. Carbon dioxide still makes up 95% of Venus's atmosphere. It superheated our twin planet to the point where its water boiled away into space. And yet, this didn't happen on Earth. David Crisp believes that was down to a chance event.
If Earth kept all of its initial atmosphere, it probably would have turned out a lot more like Venus. But that didn't happen. We were the victims of a very lucky accident.
Earth's big break came 4.5 billion years ago. Back then, the solar system wasn't limited to the 8 planets it has today. Instead, a swarm of protoplanets, or planetesimals, orbited the Sun like bees around a honeypot. One Mars-sized body was heading straight for Earth. In a colossal cosmic collision, it slammed into our planet, creating our moon, and according to Crisp, removing the atmosphere that still blights Venus. This ancient event was the defining moment for our atmosphere. With the original deadly gas mix blasted away, our planet's air could slowly evolve into what it is today.
We were left with this atmosphere made of molten rock and vaporous rock. It took millions of years for that atmosphere to fall out and to be replaced by an atmosphere made up of nitrogen and carbon dioxide and water vapor.
These new gases came from above and below. Volcanic eruptions spewed out fresh stalks of nitrogen and carbon dioxide from within the planet's molten core. While the vital element of water may have been delivered by icy comets, each impact bringing a new supply of frozen liquid. But the air still lacked one of its key ingredients.
One of the things that was missing is free oxygen, molecular oxygen, O2, the stuff we breathe.
Dr. Janet Seifert of Rice University in Texas searches for the event that produced the atmosphere's final element.
We know from the rock record that for the first half of Earth's life, there was no oxygen in the atmosphere whatsoever. There were greenhouse gases like methane and CO2, but there was no oxygen.
But the rock record shows a sudden change, dated to around 2.5 billion years ago. Evidence of the first oxygen in the atmosphere. The gas was released by a humble microscopic living organism called cyanobacteria.
Well, it turns out cyanobacteria are the only things that can actually produce oxygen. So we know that at some point cyanobacteria colonized enough of the planet in order to produce enough oxygen that it became resident in the atmosphere.
As the microbes multiplied and spread, the gas built up in the air, transforming the planet in a process known as the Great Oxidation Event.
Oxygen is very powerful. The world gets turned upside down. Everything has to begin to adapt to now a completely new atmosphere where oxygen is dominating.
First, the oxygen reacted with the oceans, causing iron within them to form rusty deposits on the sea floor. Then its effects reached dry land. It reacted with soil and rock, giving them a reddish, rusty tinge. And once these minerals had absorbed their fill of oxygen, the gas began to gather in the atmosphere, with dramatic consequences for life.
Complex animals could have much higher metabolisms because of the sheer potential that oxygen provided for them, and a whole different kind of evolution was able to take place.
Powered by oxygen, life evolved from single-celled organisms to complex animals. And plants also began releasing oxygen, thanks to an ancient adoption of photosynthesis.
A very ancestral, primitive plant cell either engulfed or tried to digest or surrounded a cyanobacterium. And instead of digesting it, it actually became an organ within the plant. So every bit of the oxygen, even if it's coming from a plant that you see in your yard, is coming from an ancestor of a cyanobacteria resident inside the plant.
With the rise of oxygen, the air's unique blend of gases was complete. This air we breathe has changed planet Earth, molding its terrain and habitats. And as we continue our upward journey, we run into another vital substance: water. The turbulent movement of our atmosphere carries water vapor around the globe. Powerful winds and violent storms smash our buildings and drown our fields. But without them, the land would be bone dry. Our atmosphere is in constant motion. The moving air that causes our weather circulates between the ground and 50,000 feet. It is the sun that drives this movement. When solar energy reaches Earth, it heats the surface and atmosphere, but it does so unevenly. This temperature difference causes the air to move. Hot air near the equator expands and rises. Cold air at the poles becomes denser and sinks. NOAA's Marty Ralph can track its movement over the globe on the revolutionary Science on a Sphere simulator.
What we're seeing here is a portrayal of the Earth's surface temperature, and red and warm colors are warm temperatures like we see in the tropics here. Up in the poles, you see the blues and the greens. Those are the colder surface temperatures. So we can watch this and actually see the warm air moving northward, the cold air moving southward, and we can see the changes in the seasons.
If the atmosphere didn't move, the poles would be 45 degrees cooler and the equator 25 degrees warmer. The great deserts of the Sahara, Atacama, and Mojave would expand dramatically. Northerly cities like London or Boston would be locked in an icy winter. It is only the atmosphere's circulation that prevents this. It regulates the temperature, moving the air to create the weather that covers our globe. The planet's rotation twists the air as it flows, helping form the hurricanes that lash the coasts. As moist air wells upwards, clouds become electrically charged and send lightning bolts crashing down to Earth, superheating the air to 18,000 degrees. And as the air cools, water vapor condenses into clouds and rain. This water evaporates from the world's oceans. At any moment, 0.1% of the world's water is being carried in the air. But that tiny percentage adds up to almost 3,000 cubic miles of liquid. If the air didn't carry water, the land would be bone dry.
Storms do a really important job for the atmosphere. They help reduce the difference in temperature between the poles and the equators. And in the process, they actually create the rain and snow that we depend on.
One of the most powerful weather systems is a newly discovered set of water channels running through the air. Ralph's current research focuses on these mysterious rivers in the sky.
One of the phenomena that really influences where the water is available for us are these regions where water vapor transport is focused. We've come to recognize that phenomena as an atmospheric river.
Atmospheric rivers are narrow channels of hurricane-force winds that can stretch for thousands of miles. A single river can carry 3 times as much water as the entire Mississippi. They provide almost half the annual rainfall for parts of the American Pacific coast, but when they remain over one area for a day or more, they can produce violent flooding.
Heavy winds, lots of water vapor, a storm track that's not moving fast adds up to a big flood event.
The rivers were only recently discovered because they form over the world's oceans. We still don't have enough data to forecast their floods.
An example of the challenges we face in weather prediction is that while this model can actually produce an atmospheric river, like we're seeing right here, a week ago today we looked at the forecast for today, and it said there should be a strong atmospheric river creating heavy rain in Northern California. Well, instead, it's hitting Canada. That's a huge difference.
To fill the gap in data, Ralph explores the rivers on research flights. The rivers form in front of banks of cold air. They create channels of wind that carry huge quantities of water vapor from the ocean to the coast at up to 100 miles an hour.
These are like conveyor belts for water vapor. They're very narrow, and yet they do 90% of the water vapor transport for the global atmosphere at those latitudes.
When the airflow hits a mountain, it rises up, shedding its water as rain and snow. Ralph has tracked how the rivers move with the changing seasons. But to fully forecast the floods, he needs a lot more atmospheric data. He believes robotic drone aircraft, developed for the military, could continually measure the air over the oceans, charting its temperature, winds, and humidity. And the flights could also track how the rivers are changing.
We're starting to see evidence that the more intense atmospheric rivers might become more frequent in certain parts of the world, and that will contribute to increasing the frequency of flooding.
The changes Ralph has identified are part of a wholesale shift in our climate and atmosphere. Deserts are expanding, while rainforests are drying out, all due to a change in the chemical makeup of the air. This blend has always been in flux. We alter the proportions with each breath we take. But our factories and homes, planes and cars, amplify the process. For over 2 centuries, we have been dramatically increasing the amount of warming carbon dioxide in the atmosphere. So far, the planet's natural air filters have pulled nearly 55% of it out of the air.
The North Atlantic has absorbed a tremendous amount of carbon dioxide, but at the moment it's almost completely saturated by carbon dioxide, so it's not absorbing very much more. It's almost like a bottle of some kind of soda pop. If you warm it up a little bit, it'll actually fizz and release CO2.
As these natural safety valves close, we will face an even more dramatic rise in temperatures. The global average could be up 7 degrees Fahrenheit by the end of the century, wreaking havoc with weather patterns and habitats. We can prevent climate change by preserving the air's delicate blend of gases, the unique mix that sets Earth apart. And our planet is also marked by how this blend sits above the surface in a distinct layered structure. As we rise above the clouds and winds of lower altitudes, we enter a completely new zone. A world of extreme temperatures and ever-thinning air. Air that would kill us in seconds, but which shields us from deadly radiation. We live in a tiny sliver of Earth's atmosphere called the troposphere. Winds and clouds, rain and snow dominate this turbulent zone, but above it lie miles of freezing dry air. The conditions there would kill a human in seconds, but we desperately need the high atmosphere's weight and protection. Engineer John Powell's balloon team has spent 27 years exploring its layers, pushing further and further into this remote, dangerous world.
Sometimes we just run into a phenomenon that we have no idea what that was. We just have this moment of data in it that we need to go back and explore. But it really is like a completely alien, foreign world up there.
The team has made over 90 launches. Each one edges them closer to their ultimate goal of reaching space.
You can use balloons not just to go to the edge of space like we do now, but go all the way over the line and actually use balloons or airships to go all the way into space. Space travel without the rocket.
Officially, the atmosphere ends and space begins 62 miles up. This sounds high, but on a tabletop globe, that would only be as thick as the coat of varnish. And in reality, the air extends out much farther. The atmosphere's lowest layer, the troposphere we live in, ends 40,000 feet up, the cruising altitude of airliners. Above are another 4 distinct layers.
They're all separated by their temperature. It gets colder and colder and colder, then it warms up to a nice toasty 0, and then it starts to get colder again. So whenever the temperature changes directions, you know you've made it into another layer.
First comes the stratosphere, a stable layer without strong winds. Then temperatures in the mesosphere plunge to minus 150 degrees Fahrenheit. Above that is the thermosphere, where solar radiation can push the thermometer back up to 4,500 degrees. And finally there is the exosphere, an endless zone where air molecules slowly thin out into the pure vacuum of space.
Now the exosphere is really high. They actually detected particles of the Earth's atmosphere on the far side of the moon during the Apollo program.
As Powell's balloons rise towards space, they leave the world we know far behind. The air thins, and they begin to lose the protective weight of the miles of air above them.
The pressure is dropping. When you finally get to the stratosphere, to the altitude we like to work at, it's only 1/100th that of it is on the ground. It is a whole different world than down here.
The weight of the miles of air above us creates air pressure. We often think of air as weightless, but all those gas molecules add up. Grand Central Station's main concourse contains over 200 tons of air. As gravity pulls the air down, it compresses the layers below, making them denser. This dense air is what we are used to dealing with on the ground. Just a pint of it contains more than 8.5 billion trillion gas molecules. But higher up, around the balloon, there is less atmosphere pressing down from above. The air up here is thinner.
It's like being under 1,000 blankets, and each blanket is a layer of the atmosphere. And we're being pushed under all of these blankets. Now, as you go higher, you're going up through the blankets, so it's pushing on you less, until you're at the top and above most of the blankets where you don't feel it at all.
That thin air seems alien to us because our bodies and technology are so perfectly adapted to thicker air. We even need it to hear. The gas carries sound through air as pulsing waves of pressure.
Sound is just a wave, like a water wave in a pond. But if you take away the water, there's nothing for the wave to go across. And as the atmosphere gets thinner and thinner, it supports that wave less and less and less.
Finally, in the vacuum of space, there is nothing to carry the wave. And even the largest explosion is silent. School science experiments on board the airship study the dramatic pressure change.
And we call it a PONGSAT, for ping pong ball satellite. And it's real simple. The first thing they do is they have to cut the ping pong ball in half. Then your experiment goes inside. And the simplest and my favorite is where you take like a little mini marshmallow and they just drop it in the ping pong ball. This is satellite construction at its best. And then we take them to the edge of space.
In the thin air of the stratosphere, the marshmallow is no longer held together by high air pressure. Air bubbles inside it expand, causing the spongy candy to bloat outwards and burst open the PONGSAT. Just as the thin air is dangerous for marshmallows, it can also affect flesh and blood. Contrary to popular belief, your blood won't boil. It's held in by your blood vessels. But any exposed flesh will swell out like the marshmallow. And at around 26,000 feet, the air is too thin to breathe. There just aren't enough molecules in every lungful of air. And starved of oxygen, your brain will begin to shut down.
You know, the extreme cold would get you, but the lack of pressure would get you first.
As the balloons rise higher still, they face attack by an invisible bombardment, radiation. Every day the sun radiates a titanic amount of energy, some of it in the form of high-energy ultraviolet rays. These rays pack a powerful punch, and in the high atmosphere, they attack the structure of Powell's balloons.
The UV literally damages the material, and you start getting microscopic cracks in the material, which makes it brittle. You know, eventually it just fails, and the balloon pops.
The rays are potential killers, both for balloon and human. They bombard our cells and DNA, triggering cancers. But around 7 miles up, a layer in our atmosphere shields us from 99% of these rays. It is made up of ozone, a rare molecule of 3 bonded oxygen atoms. This can absorb and block high-energy UV rays.
The ozone layer, it's not like this saran wrap thick layer, a boundary that you pass through. It's actually miles and miles thick, so it's a slow diminishment.
Man-made chemicals used in refrigerators and aerosols have been eating away at this delicate protective layer. Every winter, holes in the shield appear over the poles. The harmful chemicals are now banned, and the layer is beginning to recover. And above it, the fragile air of the mesosphere is shielding us from another deadly barrage from space. In East Texas, Jeff Notkin and Steve Arnold are searching for the remains of cosmic missiles that have been shattered by our atmosphere. fragments rarer than diamonds and worth their weight in gold. Meteorites. These two professional hunters seek out space rocks buried in the fields and prairies.
This search for meteorites allows me the chance to touch a little bit of what's from out there, bits of the cosmos that have found their way to us.
The hunt has taken Steve and Jeff from Siberia clear down to Chile, and some of their finds have been spectacular.
The largest meteorite I found was 1,430 pounds. It was a large stony iron meteorite from up in Kansas. We didn't realize it was that big of a deal. The media kind of picked it up and ran with it.
He's very modest. It's not only Steve's greatest find, it's one of the greatest finds ever made in meteorites.
The massive space rock has been valued at up to a cool $1 million. But this is a rare find because most meteorites simply don't survive a brush with Earth's atmosphere.
Most of them don't make it to the surface. The atmosphere is our friend in the sense that it protects us from these rocks from space, but for meteorite hunters it's also not our greatest ally because it burns up a lot of what we're looking for.
Steve and Jeff search for remaining fragments using a custom-built metal detector rig.
Meteorites will have iron in them, and it's ferrous, and so not only will a magnet attract to it, but also a metal detector will be able to pick it up.
Every year, over 18,000 meteorites lock onto a collision course with Earth.
When meteorites encounter our atmosphere, they're traveling at the speed that they acquired while moving through the vacuum of space. And typically, they're traveling at many thousands of miles per hour.
As they head down to Earth, they cut through the outer reaches of our atmosphere. But once the meteorites enter the mesosphere, the air starts pushing back.
We can't see the air around us, and we can only feel it on really windy days like this. But a meteorite encountering our atmosphere definitely feels the air, and that is because it's traveling so quickly. When it encounters our atmosphere, the air in front of the meteorite cannot get out of the way in time. It's almost like the meteorite hitting a solid wall, like a block of concrete.
As the air in front of the meteor compresses, it also heats up to more than 30,000 degrees Fahrenheit. Eventually, it bursts into flame, lighting up the sky. When you see a falling meteorite or shooting star, it's actually the protective shield of air that you see burning, not the meteorite itself. But the friction and heat wears away at the space rock. The hot air actually melts the metal surface. And often the collision with the atmosphere can have a shattering effect, splitting the meteorites along fissures.
This is an actual meteorite, and if this were to encounter the atmosphere at high speed in its current condition, and that's the result.
Only fragments of the original asteroids survived the fall to Earth. Their speed has dropped from 17,000 to 300 miles an hour. Rocks as big as station wagons have shrunk to the size of golf balls. They impact on the surface, forming holes a few inches deep. The chances of finding one are remote.
There we go.
I'll get the shovel.
Right about there, Maestro.
It looks promising, but this time the guys are out of luck.
So yeah, we found a plow, and basically a lot of different types of trash can be in these fields, and so anything that's ferrous, our detector's going to pick up. Meteor wrongs, as we call it, as opposed to a meteorite.
On average, they uncover 75 meteor wrongs for every meteorite.
This is a genuine iron meteorite. This is believed to have once been part of the core of a long dead planet or asteroid. And this was found right here in this strewn field. These remarkable little shapes indentations on the surface are called thumbprints, or scientifically regmaglyphs, and that's a feature that's unique to meteorites. And these little markings are caused by the surface actually melting as it flew through the atmosphere. We don't find regmaglyphs on Earth rocks.
The air is constantly at work, making meteorites rare and valuable.
The chances of meteorites surviving their journey through the atmosphere and being found are minuscule. If it wasn't for our atmosphere, we would have little particles raining down on us all the time, and some of them not so little.
The mesosphere's barrier of thin air is the final gift from our atmosphere, adding to the oxygen we breathe, water we drink, and pressure we feel. But as we cross into the layers above, we leave life far behind. John Powell's airships have only reached the upper stratosphere. Kittinger's jump point is below that, in the middle of the stratosphere. The only people who travel through the superheated thermosphere and distant exosphere are astronauts, heading for space. One day, these manned space missions may reach out even further, to distant planets with alien atmospheres. Atmospheres that may support their own life forms. Elsewhere in our universe, on distant planets, alien air may support extraterrestrial life. Joel Hagen has spent 20 years imagining how those atmospheres could have affected their inhabitants.
That's where some of the real creative joy comes from, is trying to think about everything that has happened here and then take yourself one notch beyond it and imagine, what haven't I seen yet? And then try to visualize that.
One of the possibilities that intrigues Hagen is life on a gas giant planet.
This is an environment so completely alien to what we're used to. Even a planet like Jupiter, for instance, has no solid surface, just a gradual transition of densities of gases. And I think we might imagine creatures in an atmosphere like that sort of relied on buoyancy, perhaps being able to generate hydrogen, for example, somehow within their bodies.
These creatures would be like hydrogen-filled blimps, lighter than the air, able to float amongst the gas clouds.
The concept that I have here is to have perhaps colonies of microbes in these sort of tentacle-like structures here. And these microbes generate the hydrogen, which in turn sort of inflates the gas bag here. A creature like this then could sort of float freely at certain levels in the atmosphere.
On other planets, with denser atmospheres, larger, more complex creatures could take to the skies. The thicker air would support them aloft, allowing bulky reptiles to glide and fly.
This creature probably wouldn't be able to fly very well on our planet, but even on a planet like Titan, for instance, it has a surface gravity only about 15% of Earth's, but an atmospheric density at ground level about 1.5 times. Even a person with wings strapped to their arms could fly in an atmosphere like this, so we could have creatures like this.
Hagen bases his ideas on known planets and the evolutionary history of Earth. But it's all pure speculation, until we find life in alien atmospheres.
I would be pretty thrilled just to find microbes under rocks on Mars, for instance. They don't have to walk up and shake hands with me to get my blood up. I would be pretty happy just to know that life has happened twice.
At present, we are alone. Life may have happened just this once. And if it did, then it's only because of our planet's unique atmosphere. As we have soared for miles above the ground, we have journeyed through this ocean of air. The air which shields us, supports us, and sustains us with every breath. Abundant life. It's the hallmark of our planet. But it's water that makes us unique.
Liquid water is the essential environmental requirement for life on Earth. So when we look for life elsewhere, we start first by looking for liquid water.
Our search has taken us to an alien world that seems to defy the laws of physics. A place where water can't exist, but shows us evidence that it might.
We have what we in science call an anomaly.
NASA's Phoenix lander will find out if life is possible on this desert planet. Welcome to Mars, the water world.
Load relief kit crate is in, vehicles responding. Vehicles recovering very nicely from the liftoff transients.
August 4th, 2007 at 5:26 a.m. This Delta II rocket blasts off from Cape Canaveral. In its nose cone is NASA's first robotic Mars scout, the Phoenix lander.
At this point, we have a strong signal from Phoenix via Odyssey.
At NASA's Jet Propulsion Laboratory in Pasadena, California, engineers monitor the progress of the $500 million mission.
All stations, we have confirmed crew stage separation and UHF signal acquisition via Odyssey. Atmospheric entry on my mark. 3, 2, 1, mark.
The new generation lander enters the final phase of its 400 million-mile journey to Mars.
1 minute since LOS, standing by for signal reacquisition.
Phoenix will search the Arctic plains of Mars for the building blocks of life, including carbon, nitrogen, and most importantly, water.
Touchdown detected. Landing sequence initiated.
Phoenix intends to prove that life on Mars is, or was, possible. If it does, then life on Earth is not unique. This is a test simulation, but on May 25th, 2008, the team at JPL attempts this for real.
Primary objective of Phoenix is to explore the Martian Arctic and to determine whether or not conditions for life are there today or existed in the past.
If Phoenix finds what it's looking for, it will change our understanding of the solar system. If there's life on another world, it could mean that the universe is teeming with it, that the aliens of our science fiction could be a reality. Phoenix might even find them. But finding the signs of life on a planet millions of miles from home is an incredibly difficult challenge. The lander hasn't been designed to find life directly. It's been built to find the necessary ingredient for it: water. Chris McKay is a planetary scientist at NASA's Ames Research Center.
When we look at life on Earth, we see an enormous diversity. Organisms that do all sorts of different chemistry, live in all sorts of different environments, but the one thing that all organisms on Earth have in common is a requirement for liquid water. So naturally, when we look for life elsewhere, we start first by looking for environments that have liquid water.
Here on Earth, wherever there's water, there's life. Even in temperatures as extreme as 14 degrees Fahrenheit, organisms can survive. So if we find signs of water on Mars, we might find life too. But why are we looking on Mars? Professor of Geomorphology Vic Baker explains.
30 years ago, a spacecraft called Mariner 9 produced about 9,000 pictures, many of which showed large channels and valleys. And it was very obvious that these channels and valleys are directly analogous to what we see on the Earth, formed by water.
Scientists are stumped by these images. It definitely looks like water erosion, but as far as they know, there is no water on Mars. Its atmosphere is too thin to support it. The air pressure on Mars is less than 1/100th of the Earth's, which means the air on Mars's surface is the same as it is here on Earth at 110,000 feet above sea level. That's 20 miles high, nearly 4 times the height of Mount Everest. Scott Rafkin is a planetary atmosphere specialist at the Southwest Research Institute in Boulder, Colorado.
It's fairly common knowledge that if one goes camping or hiking and you go up to higher altitudes and you go to boil your water, as you go higher up, it boils at lower and lower temperatures. That change in altitude is what you're really doing is changing pressure. As you go up in altitude, the pressure is becoming less and less. And so what happens is that as you go higher up, it becomes easier to boil water. You don't need to raise its temperature as much.
This experiment shows the effects of Mars's atmospheric conditions on water. Gradually removing air from the chamber reduces the pressure. At first, nothing happens. But when the pressure drops to the equivalent of Mars's atmosphere, the water boils. Water normally boils at 212 degrees Fahrenheit, but at this low pressure, it boils at room temperature. On Mars, this happens at just 50 degrees.
The stability of water on any planet is tied to primarily the pressure. And the pressure on Mars is so low that if one could have liquid water sitting out on the surface, it would simply boil.
Mars's ultra-thin atmosphere creates another problem for water to exist here. There's not enough of it surrounding the planet to insulate it. Mars is ice cold. At its warmest, it's just 70 degrees Fahrenheit. At its coldest, the temperature drops to -225.
Now, of course, on Mars we have another problem, which is that it's very, very, very cold. So even if one had the higher pressure so that the water wouldn't boil off, it would just freeze solid, like a rock.
The existence of these channels and valleys that appear water-carved baffles scientists.
The question is, how do you have these two things? How do you have a planet that is cold and dry with a thin atmosphere, and yet clearly, in its past, had flowing water?
Over the years, scientists have offered many theories to explain the features seen on Mars's surface.
People have suggested, well, maybe it's carbon dioxide liquid, or maybe it's lava, or maybe it's wind. Well, wind, lava, carbon dioxide could have formed many of the features we see on Mars, but they can't explain all the features.
And for the past 30 years, this has been the major source of science controversy. And it's the reason that the current NASA program is sort of directed with this euphemism, follow the water.
Using the latest science provided by Phoenix, NASA hopes to prove once and for all that they were made by liquid water, a substance that shouldn't exist on the planet. But the debate is growing more controversial. In June 2000, scientists got very excited about these images taken by the Mars Orbiter camera, a probe that has been circling the red planet since 1997. This one was taken in 1999, and this is of the same location in 2000. The images clearly reveal a changing landscape. To geologists like Vic Baker, these recently formed features look strangely familiar.
On Earth, we would call them gullies. They're sort of on the scale of hundreds of meters, no more than a kilometer. They're patterns like the veins in a leaf or branches in a tree that result from how water falling on the surface organizes itself into larger and larger drainages.
These gullies and alcoves seem to have been recently formed by water. They have appeared in the southern hemisphere of the planet, on slopes that get the least amount of sunlight during each day, one of the coldest parts of Mars. Their similarities to gullies formed by water here on Earth defy logic and the laws of physics. So what created them? Did water flow across Mars in its past? And is it still flowing today? On May 25th, the Phoenix lander, NASA's $420 million mission to Mars, touches down on the red planet to answer two questions that have vexed scientists for decades. Is there water, and could there be life? At the heart of this debate lies this rock that landed on Earth from Mars. Discovered in 1984 in the Antarctic, it's 6 inches long and weighs over 4 pounds. It's called the Allen Hills meteorite, and it's one of just 34 Martian rocks that have been found here on Earth. Johnson Space Center astrobiologist Dr. David McKay has studied this meteorite for more than 10 years.
Allen Hills is unique among the Mars meteorites because it's so old. It is by far the oldest of the known Mars meteorites. And furthermore, with an age of 4.5 billion, it is older than any rock ever found on the Earth.
McKay believes it contains proof life was possible on Mars. Using high-resolution scanning electron microscopes, he examines the meteorite and discovers tiny globules of iron and magnesium carbonate. Elements almost certainly formed and deposited by liquid water.
Carbonates are significant because they show that not only was water there, but it was relatively low temperature.
McKay is convinced that this proves Mars's atmosphere was once very different and could sustain flowing water, so the conditions for life were present. By radioisotope dating the carbonate globules, McKay comes up with a figure. Water flowed on Mars 3.9 billion years ago. NASA's current crop of rovers scouring the planet backs up McKay's findings. This is Meridiani Planum, the landing site of the rover Opportunity in January 2004. It's a dusty area the size of Oklahoma. Photographs relayed back to Earth reveal the soil is littered with countless BB-sized rocks. NASA scientists nicknamed these puzzling objects blueberries. On Earth, similar deposits form, but only in standing water or hot springs. Geologists have uncovered blueberry-like clusters dating back millions of years in Lake Superior and near the hot springs of Yellowstone National Park. Their discovery on the vast plain of Meridiani Planum suggests this area was once saturated with water, or was even an ancient lake. In fact, closer examination of the surface of the planet reveals that much of it was once a water world. These images, taken by a high-resolution stereo camera aboard the Mars Express spacecraft, reveal Mars's watery, almost Earth-like past. This is a large depression called Ioni Chaos, and next to it an outflow channel called Aris Vallis. They're the remains of Martian river systems, and to planetary geologists like Jim Rice, clear evidence of ancient catastrophic floods.
We took every river on Earth and put it in one spot, had them flowing at the same time. Some of these flood channels on Mars, when they were in full force, were 20 or 30 times bigger than those.
What was it that happened in the Martian past? Why do we have a planet today that is very cold and dry and gives every indication that we don't have liquid operating on its surface? Why in the past did we form these channels?
If Phoenix can figure out if water flowed across the surface of Mars in the past, it will explain the valleys and canyons we see today, and take us one step closer to discovering if water still exists, and even life. Now the Phoenix mission can confirm what the experts suspect.
It must have been warmer, at least for some period of time, so that we could have liquid water on the surface. And the pressure must have been higher than it is now, or the water would have boiled away.
Early in its evolution, Mars was much warmer. In fact, it was boiling. $4.6 billion years ago, our sun bursts into life, and our solar system forms around it. Both Earth and Mars are huge balls of lava, boiling at over 12,000 degrees. Slowly, they begin to cool. Dr. Peter Smith heads up the Phoenix mission from its base at the University of Arizona.
Earth and Mars formed at about the same time, but Mars is only half the diameter of the Earth, and therefore it would cool more rapidly.
Mars's size proves to be the crucial factor in its transition from a fiery molten ball into a warm and wet planet. In this demonstration, two globes are used to represent Mars and our own planet, Earth. These scale models exactly replicate the difference in size of the two planets. Mars, shown here on the left, has half the diameter of Earth. Both spheres have been heated to the same temperature. Now they are cooling naturally. Infrared time-lapse clearly shows how quickly the smaller sphere representing Mars cools. Mars was cool enough for water at a time when Earth was still a red-hot ball. This water comes from comets. The early solar system is littered with large asteroids and comets made up of ice. As they crash into the planets, the ice melts. On super-hot Earth, the water boils away instantly. But Mars is cool enough to hold on to the huge quantities of water released by impacts.
And in that cooling, liquid water would be stable on the surface long before it would be stable on the Earth. And so during that period, it may be that you had rains and valley systems and lakes and all kinds of Earth-like situations.
Scientists believe that 3.9 billion years ago, Mars had the climate and atmospheric conditions to support liquid water, an essential ingredient for life.
Now, in the early days of the history of our solar system, this planet, the Earth, was not a good place for life to develop. We had noxious gases all over the places, volcanoes belching out all sorts of stuff. Mars was warm and wet and wonderful. It was the most likely place for life to develop.
Today, Mars is no longer warm, but is it wet? Understanding what happened to Mars's water is the primary goal of the Phoenix mission. Its success might hold the key to answering a 30-year-old question. Does water still exist on Mars? Scientists are now certain that Mars was once warm and wet. Pictures of ancient riverbeds, blueberries on the surface, and carbonate globules inside the Allen Hills meteorite confirm this view. But if there was water billions of years ago, where is it today? The question of whether water still exists on Mars will only be settled when NASA physically finds it. And that's the job of the Phoenix lander. It's being sent further north than any previous mission, to a site chosen because frozen water might sit below the surface. In 2003, NASA's Odyssey orbiter produces this image. Using its gamma-ray spectrometer, the spacecraft maps levels of hydrogen in the upper 3 feet of Mars's surface. Since high levels of hydrogen indicate the presence of frozen water, scientists think that these blue and violet areas, the densest concentration of the element, reveal an enormous frozen reservoir.
In fact, there's so much water in the polar areas and the nearby ice terrains that if you spread that water around the surface of Mars, that alone would inundate the surface of Mars on the order of 6, maybe 10 meters deep.
Phoenix's first job is to confirm that the hydrogen-rich area is in fact made up of water. Then scientists can begin to piece together the chain of events that lock the water under the planet's surface. Maybe then they'll begin to understand how the recent wet spots appeared. Some scientists believe they are a remnant of ancient climate change. Mars cools much more quickly than Earth, allowing water to exist on its surface. But a drastic shift in atmospheric conditions means it can't hold on to it. Earth's large molten core generates a magnetic field which protects our atmosphere from solar radiation. But Mars's small core cools so much that it no longer produces an effective shield. Solar wind blasts away its atmosphere and most of its water. Pressure falls and the temperature plummets. Whatever water it has boils away or freezes solid, leaving the Mars we see today, a frozen world. Up until recently, scientists believed that Mars's core is so cold that it is no longer able to crack and move the planet's surface.
The Earth releases a lot of its heat continuously by a process that's known as plate tectonics, where the continental masses of the planet are actually shifted by the formation of new crust in the ocean basins. Mars doesn't have that.
But the discovery of the gully features, the wet spots, suggests that Mars's core hasn't cooled as much as they thought.
Because it can't release its heat as efficiently as Earth, one idea is that this heat builds up with time, and episodically there's kind of a burst of heat release that will melt the ice in the Martian permafrost. And that water comes onto the surface, perhaps associated with gases that change the composition of the Martian atmosphere to a greenhouse kind of condition. So you have a temporary, unstable state where Mars